Hello, everyone. Good morning. Um, Welcome to the third day of the GeoNetcast Americas training for Eastern Caribbean states. And before we start, please run the first code cell of the homework notebook. So when we start the homework reflection, your notebooks will be ready, okay? And another comment is that I would like to thank you for your emails. Received emails from participants that were able to finish the procedure available in the complementary activities session in the Moodle page. And some were able to run Python scripts locally in their own laptops. Also, some participants were able to create the channel differences in the homework activity, and that is great. I have also received emails from participants that had problems and have not managed to finish the procedures, and that's also okay. If we do not find a solution until the end of the training, we will keep working and exchanging emails until we find the cause of the problem. But the important thing is that you try it and understand what is needed to start developing your own products for your med services, okay? Thank you very much for your emails. Renzo, Enwa, Dale, Eugene, Cassian, the others. Also, at the end of the next day, we will propose an activity with advanced animations, and we will need some tools installed in your laptops. So please try or keep trying to finish the procedure available in Moodle for the installation of these tools needed to run Python scripts in your laptop. And let me know if you have any problems. Okay, and this is the activity you need in the end of the fourth day and on the fifth day, okay? In the second day, we have seen the basic components of a GeoNetcast Americas station and the functions of each one of these components. We have also started to explore each component in more detail, starting with the antenna, the feed, the filter, and the LNB. And we have also learned how to get the antenna pointing parameters using the dish pointer webpage, like the azimuth, elevation, and LNB skew angles, and practice a little bit. In the second part of the Python hands-on, we have seen how to read parameters from the NetCDS metadata, how to add a shapefile to our plots, how to overlay GeoLAM lightning detection with ABI images, how to create RGB composites and download data from the cloud, which opens lots of possibilities. And at the end of the day, we have proposed some homework activities with 4 channel differences and 4 RGB composites. And today we will start with the Python homework reflection. Okay. And we will review the first 2 channel differences in the homework COLAB notebook, the night fog difference and the split cloud phase. And after that, we will see the GeoNetcast Americas disaster capabilities. We will explore the S300D DVB-S2 receiver in detail and learn how to check the GNC-A reception parameters. And in the Python hands-on, we will see the first part of the numerical weather prediction data processing example script in Google COLAB. Okay, so before starting with the disaster capabilities, let's go to our GOZAR homework COLAB notebook and create the night fog and split cloud phase differences. Okay, let me open it here. And I really want you to follow with me, right? You may download, example, you may access the original COLAB notebook here. In the end of the second day, there's an assignment called Creating Channel Differences and RGB Composites with Python. Okay. And you should create a copy. And here I have called my copy Diego_homework and the original name. Okay. And the first step is to run this first code cell. It takes some minutes And that's why I have suggested you to run the first cell that installs the necessary libraries and download ancillary files in the beginning. And this cell installs the netcdf library here, use it to read our files, and the cartopy library, use it to add maps to our plots. It also installs the boto tree library, use it to download data from the cloud. It also downloads the utilities.py script. And as we have seen, it has some useful functions. And in this cell, we also download the shapefile with the provinces and states. And as an extra, we also create two folders called samples and output. We create these two folders in our virtual machine here, output, samples. And in the samples folder, we will store our netcdfs. And in the output folder, we will store our plots. Okay. But we may also create these folders directly in our scripts, as we have seen, using the OS library, the operating system library from Python. After that, we have a reference table, because we will be manipulating different channels. So if you want to take a look at the wavelengths and resolutions, for example, you have this reference table in your notebooks. And then we have three examples, right? The first one, a channel difference called the split window difference, which is useful to identify gradients in moisture or detect moistening in the atmosphere and identify regions of low-level dust. As we have seen how to create one during the second day. In our second example, we have the ARMAS RGB, and we have shown how to create it in detail during the second day. And the difference between this example and the example seen during the second day is that we are downloading data directly from Amazon. And so we may create this RGB for any date. In all the examples from this notebook, we can create and download data from any date, as long as it is available in Amazon, okay? In this third example here, we have the day cloud phase distinction RGB. And if you open VSAT or slider, you may access this RGB here. Day cloud phase or cloud phase from GMA. This recipe has been developed by GMA. And here it is. And we see in this example how to create this RGB here. And it is one of the most used RGBs by the community. It uses and it is simpler than the ARMAS RGB because it uses, as you see here, a single band in each component. Band 13, the 10.3 micron band as the red, band 2, green, and band 5 is blue, right? And one thing I forgot to mention in the second day, and a very important detail to consider when creating RGBs is that we need to consider the resolutions of each band, because when we stack here, when we create a stack to combine RG and B composites, right? Data from each component must have the same dimensions. Must have the same dimensions, okay? For example, in the ARMAS RGB here, all four bands used to create the RGB are 2 kilometer bands. So they all have the same size, and we didn't have any problem. However, in this third example, we are using bands 13, which is a 2 kilometer band. We are using band 2, which is a half kilometer band. And we are using band 5, which is a 1 kilometer band. Okay, so each component has a different resolution. And if we just read the channels as they are, we will get an error when trying to stack the R, G, and B components because they have different dimensions. So when creating an RGB, the final composite must have resolution of the band with the lower resolution. That's a rule, okay? And in this case, we have 2 kilometer, half kilometer, and 1 kilometer. So somehow we need to read the data from the half kilometer band and 1 kilometer bands in such a way that they will also have the same size of the 2 kilometer band, okay? And here's how we do that. Here. Okay, I will repeat that. When creating an RGB, somebody has asked me to repeat this in the chat, and I will repeat it. When we create an RGB, remember that when we are stacking bands, let me zoom in. After we make all these calculations, right, we need to stack. That is, we need to combine these three components, the R, G, and B, right? And to stack, we use the numpy stack command. However, the numpy stack command only works if my R component, G component, and B component have the same dimensions, right? The same number of rows and columns, okay? In the RMAS RGB, here, we are using 4 bands, okay? And all these 4 bands, band 8, 10, 13, and I forgot the other one. Band 8, 10, 12, and 13. If we look at the table, at the reference table here, 8, 2 kilometer, 10, 2 kilometer, 13, 2 kilometer, 12, 2 kilometer. So they are all 2 kilometer bands, right? So the data, the files, the net CDFs, the brightness temperature data sets, they have the same dimensions. Remember we saw in the first day 5,125 and 24 rows by 5,124 columns. All 4 files have the same dimensions, right? And that is why in the RMAS RGB, we didn't have any problems during the stack here. Because after all these calculations, I'm dealing with 2 kilometer bands, and they have the same dimensions, okay? That's the first situation. In this third example, the day cloud phase composite, we are using 3 bands, right? Band number 13, band number 2, and band number 5. Band number 2 is a 2 kilometer resolution band. Band number 13, sorry, it's a 2 kilometer band. Band number 2, right, which is the 0.64 visible band, it has half kilometer resolution. And band number 5, using the blue component, it has a 1 kilometer, it has a resolution of 1 kilometer. So each one of these bands have different resolutions. So we cannot stack them after the calculating the recipes. We just cannot stack them because when we try to stack them with the numpy stack command, we will get an error because they have different dimensions, okay? So somehow we need to read the 2 kilometer band and the 1 kilometer band, band 5, in such a way that they will also have the same dimensions of band 13, that is 2 kilometers. So when creating an RGB, any RGB, we have always to consider the lowest resolution band. And the lowest resolution band in this composite is band 13, right? And band 13, if you look at the reference table, it has 2 kilometer resolution. So somehow we need to make band number 2 and band number 5, we need to make them, we need to read them in such a way that they also have the same dimensions of band 13. Okay, let's see how we can do that, okay? remember that on the first two couple of commands, we are creating the folders, the sample folder and the output folder. And we are doing that using the make dears command of the Python OS library, okay? After that, we are finding the date. And in this case, in this example, we are downloading data from 18 June 2020, 17 UTC, okay? The next step, we need to read the 3 bands or the number of bands used to create this particular RGB. In this case, band 13, 2, and 5. And that is why when we are calling the download CMI function, download data from the cloud, we need to pass 3 parameters. And the first one is the date, the second one is the band, and the third one is where we want to store the data. And that is why here we are calling it 3 times, because we need 3 bands, okay? In the first call, we are downloading band number 13. In the second call, we are downloading band number 2. And in the third call, we are downloading band number 5, okay? Next, we are reading with the dataset command from the netcdf4 library. We are reading brightness temperatures of each one of these bands, right? Here, CMI, or cloud and moisture imagery, which is the data set that stores the brightness temperatures, as we have seen in the first day, when you open the file with Cartopy, for example, okay? And here I'm calling it file channel 13, the first file, file channel 2, the second file, and file channel 5, third file. And remember, I can give it any name I want, right? But in this example, I'm giving it file 13, file 2, and file 5, okay? Because these are the bands I need to read to create this RGB. In the next command, I'm reading the brightness temperatures, right? Using the variables command from the netcdf4 library. I'm storing this brightness temperature in the data channel 13, data underscore channel 2, data underscore channel 5, okay? And I'm calling it this way. Again, you may call it any way you want, just as long as you call the same names throughout your script, okay? And here you have the secret, and here you have the trick. In the examples from the first and second days, remember we were inserting a column between brackets, like in this first example here, a column, let me give more zoom, a column between brackets, okay? And with that, I'm saying, hey, I want to read the whole content of this data set, okay? But in this third example, as we have mentioned, we need to match dimensions of band 2 and band 5 with the dimensions of band 13, because the dimensions of band 13 is smaller than the other ones because it is a lower resolution band. In band 13, we have 2 kilometer resolution, so the dataset has a little bit more than 5,000 rows by 5,000 columns. In the 1 kilometer band here in this example, channel 5, we have the double. We have more than 10,000 rows by 10,000 columns. And in the half kilometer band, we have more than 20,000 rows and 20,000 columns. And it will just not work if you try to stack them the way they are. And that's why here, right, when I'm reading band number 2, which is a half kilometer band, I am reading it every 4 pixels. That's the trick. I am reading band 2, which is a half kilometer band, every 4 pixels. And I'm reading band 5, which is a 1 kilometer band, every 2 pixels. And I'm reading band 13 every pixel, the way we are doing before, right? And why am I reading it every 4? Because I want the dimensions to match the 2 kilometer band. So if I read a half kilometer band every 4 pixels, my final data set will have 2 kilometer resolution. And if I read a 1 kilometer band every 2 pixels, my final image will have 2 kilometer resolution. I'm just jumping pixels, okay, in order to match the final resolution. So all 3 data sets, data 13, data 2, and data 5, they have the same dimensions, the same number of rows and columns, okay? Another nice detail is how you check the size of your data with Python. And for that, you may use this shape command. And I'm going to share this command with you in the chat room. When you use this shape command, you may check, you may print the sizes of your matrices, okay? Here, I have added this print command, print data channel 13 point shape, data 2 shape, data 5 dot shape. And when I run this script, this is what you should see. My data 13 have 5,424 rows by 524 columns, okay? And that's the same for my half kilometer band, for my 1 kilometer band, because I have read the 4 kilometer band every 4 and my 1 kilometer band every 2. And now the 3 data sets have the same dimensions, okay? If you have any other questions, just send them on the chat, right? I hope that made clear this concept that in order to create an RGB, any RGBs, our component, the green component, and the blue component must have the same dimensions. And because we are dealing with bands with different resolutions, somehow we need to match their resolutions. And that's how we do, okay? That's one of the ways we can do that, okay? And after that, we are just applying the recipe. Remember that in the RMS example, we had a complicated recipe. We need to calculate one band minus the other in the R component, another channel difference in the green component, and invert the blue component, right? In the day cloud phase RGB, that's not needed. We only have one single channel per component. In red, we have band 13. In green, you have band 2. And in blue, you have band 5. And if you open the RAMB quick guide and look for the cloud phase RGB, this is what you see, right? And here you have thresholds of brightness temperature for band 13 and the thresholds of albedo for the visible bands, okay? And in our recipes, we just need to inform the minimums and maximums for each one of these composites. So minus 53.5, minus 53.5 as the minimum, 7.5 degrees as the maximum, 0% as the minimum for the green, 78% as the maximum for the green, right? 78%. 1% as the minimum for the blue, 1% as the minimum for the blue, and 59% as the minimum for the LB for the blue. 59%. Okay. With this instruction, you are just making everything that is lower than minus 53, we will keep as 53. Everything that is greater than 7.5, we will keep as 7.5. We inform the gammas, in this case, as you see here, all the gammas are 1. All the gammas are 1. We need to normalize the data, and we are doing it the same way we have done with the RMS, right? And finally, we create the stack, right? And with the stack, we combine these data sets, okay? And after that, we just do the normal, we just use the normal commands we have been using until now. Dimensions, we read the metadata with the center longitude, satellite height, and the extent of the data. We add a shapefile. We add borders, coastlines, and grid lines. We add a title, right? And we use the imshow to plot the image, right? And we pass the RGB stack. And we are creating an RGB, and that's why we do not use a color bar, and we do not need to define a color map, because the RGB itself, it's our color map that we need to interpret, right? And we are just adding a couple of titles with the date. And this is our result. Okay, the day cloud phase distinction RGB, which is available in ESAT, in Slider, in Proteus, and many other softwares, and that's how they calculate it. Okay. We can review this again on the fourth day, where we will start to the homework reflections with the RGBs. But for today, we will start with the night fog difference, which is much simpler, okay? And this is our first assignment. Create the channel difference night fog, which is band, the 10.3 micron band minus the 3.9 micron band, okay? Channel 13 minus channel 7, okay? And the first thing we need to do is copy the script from example 1, so things are easier, and we do not need to write all the code from scratch. So let's go to our example number 1. Copy the whole content of this cell. Okay, I'm just copying it. And I will paste it in my homework assignment number 1 here. Right? I've just pasted the content from the first example. Okay. Now we are going to make the necessary changes. For example, you change the title to night fog difference. Okay. I just have changed the title of my comment. And the second change, I will select a date. And for this example, I'm going to select 2023. Today is May 8th. And this is a night fog difference, so I need to see an image during the night. So I'm going to insert for UTC. Okay, 2023, 4 digits for the year, 05, 2 digits for the month, 08, 2 digits for the day, and 0400 for UTC. And I'm going to change to send you this variable in the chat box, right? Then I need to download the first band, and the first band in this case is band 13. Band 13, this is the same band from the previous example. And for my second file, I need band 7, okay, the 3.9 micron band. So I'm going to change here to 7, okay? I can use the same instructions to read the brightness temperatures, the same instructions from the first example. Let's check if they have the same resolutions. Band 13 is a 2 kilometer band. Band 7 is a 2 kilometer band, right? So I am going to subtract one by the other. And as it happens with the stacking command, I need to have the same dimension, right? Now, as I'm going to make an operation here, one minus the other, or any operations in Python, the variables need to have the same dimensions. But here I'm dealing with band 13, which is a 2 kilometer band, and band 7, which is also a 2 kilometer band. So I do not need to read the pixels every 2 or every 4 to adjust it. No, I just can read the full content of my array. Okay? Okay, right. So we have read band 13 and band 7. Okay? And we have subtracted band 7 by band 13. Okay? So that's in the data here, I have my night fog difference already. Okay? And after that, let's change some other characteristics. Color map, I will use the suggested one, gray. G-R-I-Y. And the minimum and maximum values, I'm using the suggested ones, -5 to 5, -5 to 5. Title, go 16, night fog difference. And the legend, also night fog difference. Okay, and I'll call this image underscore night fog difference, for example. Okay, and now I will run this code cell. Downloading the first file, downloading the second file, which is the prompt for my downloading function. It informs when it's downloading the file. And you should see the night fog difference. Let's wait a little bit more. Let me zoom out. And here you have the night fog difference for this night at 4 a.m. UTC. Okay, and let's see in the quick guide, night fog difference. I'm going to send this link in the chat box. As you see here, positive values, as white in our case, means clouds made up of water droplets, and negative values, clouds made up of ice crystals, okay? I have suggested gray color scale, but we can change that easily, right? And in the matplot library, we have the so-called diverging color maps, which are useful when we have to interpret positive and negative values. If we go to the, for example, matplotlib color maps page, we see that we have some diverging color maps. Let me send this link in the chat also. So let's change our color map, for example, to red, blue, RDBU, right? I'm going to the COLAB notebook and change from gray to RDBU. And with this change, we will see the negative values as red and the positive values as blue. Let's run it again. Okay. And wait. And this is what you're going to see. You should see the negative values as red and the positive values as blue. It takes a while. Here it is. Okay. And as you may see, channel differences may give us nice information. And if you look at the recipes of the RGBs, you'll note that channel differences usually are what it's used in the RGB components. For example, in this case, we have positive values, meaning clouds made up of water droplets, so water clouds with small particles, right? And if I add this channel difference to a green component of an RGB, you have an RGB that will tend to green, to greenish colors in the pixels that I have water droplets. Okay, let's change, for example, our scale to greens, and run it again, right? You see that greener the color, higher will be the contribution for a given RGB. And that's the cool part, right? If you look at for example, the quick guide from the nighttime microphysics here, let me send you the link. If you look at the recipe of the nighttime microphysics RGB, and here's the result, you see here that the greener, when I tend to dark green, I have the greatest contribution of positive values. And if you go to the nighttime microphysics, which is one of the RGBs available, look at the green component. Band number 13 minus band 7. That is the night fog difference, okay, which physically relates to particle phase and size, right? And a large contribution means water clouds with small particles. And if you look at the image here you have the greenish pixels, which are the pixels with high values resulting from the night fog difference. You see? So RGBs are useful because of that. Once you know the meaning of each color range, a single image may provide a lot of information, right? And when you master the art of RGBs, you may create very nice images, okay? Now let's open, for example, series slider. Series slider. And the default composite is called the GeoColor, right? Let me pause it. And if you look here, right, the night, you see these blue pixels. And these blue pixels are the night fog difference. Of course, only the high value, only the higher values of only the positive values of the difference. And if you look at GeoColor Quick Guide, GeoColor Quick Guide, and read the description, you see that the traditional fog product, 10.3 minus 3.9, is used to identify both ice and liquid water clouds, okay? And they are made partially transparent and placed at the top of the static city lights and background, etc. So as you may see, we are just plotting here in series slider the positive values of the fog difference, and they are visualizing it as shades of blue. And let's see how we can do that, okay? I will return my color map to red to blue, right? So we see the positive values as blue. Remember from the first day, from the second day, where we learned how we can only visualize part of the data, right? Let's do that. Data, brackets, where the data is smaller than 0, I will set all these pixels as not a number or nans, so they are not visualized, okay? Let me run the script again, and I will send you this command in the chat box, so you may try it in your own notebooks, okay? When we run it again, this is what you should see. Red to blue, the same minimum and maximums. I'm just not visualizing the negative values. This is what you should see. Okay. Now we're starting to have something similar to series slider in this example, right? Here it is. Here it is. Okay. For this assignment, I just want you to understand the benefits of having total control of the data, showing what you want to show, with the colors you want to show, and enhance the feature you want. And with the data you have available in your GNC ground stations or in the cloud, you can do this kind of manipulation. Of course, in Series Slider, they are overlaying this information with many other informations, like the true color here, or the highest cloud here during the night, and also the city lights here from views, which is a static image. But when you understand that, you may create anything you want. Okay, so that's our first example. And in our second assignment, we have split cloud phase difference, which is the 11.2 micron band minus the 8.4 micron band. And we will begin the same way we did in the previous example. Let's copy our split window difference example. So we just need to make a few changes. I will copy it, Control C, and I will paste it here, right? Let's make the necessary changes. Split cloud phase difference. Let me, and here I have the same date, right? And now I have to select the bands. Band 13 and 15, it's not right. I need the 11.2, which is band 14, minus the 8.4 micron, which is band 11. So we will just change from 13 to 14 and from 15 to 11. Okay. We need to check if they have the same dimensions. Band 11, 2 kilometer, band 14, 2 kilometer. So yes, they have the same dimensions. So we can proceed. And I will use the jet color map, jet, between minus 10 and 25. Okay. And I'm calling it split cloud phase. Split cloud phase. And I will run the script. Oh, and I will call it image split SCP, split cloud phase. Downloading the file, the first file, downloading the second file, right? And let me open the quick guide for the split cloud phase difference. Split cloud phase. Okay. And I got an error. And when I got an error, you see the play button in red and an exclamation mark here, right? And I got an error in the imshow command, right? So it has this red line here, right? And if you read the error, you see that we have an error saying hjet is not a value, it's not a valid value for the color map. So this is a typo, right? It's jet, not hjet. So I'm going to run it again. And you should see the result. And if we look at quick guide, this is the interpretation, right? Here we have our first plot, right? And here we have the interpretation. This product can differentiate between thick and thin cirrus and between cloud made of ice and those made of water. Positive value, in our case, warmer colors starting from light blue here, right? Meaning water droplets or dust, and the small negative values, large ice crystals or thick cirrus, and the large negative values, small ice crystals, thin cirrus. And the large negative here, in our example, it's dark blue. okay? And we can change the color map and scale to make these features more evident. So for example, if I change this color map, diverging color map, like spectral, for example, here, spectral, and reduce the minimum and maximum values to, for example, -5 and 5, and run it again, we can see these features mentioned in the quick guide. We can make them more evident, okay? And as I have said, these channel differences are usually components of more complex RGBs, as we are going to see. Okay, so should be, let me send you the changes I have made. And this should be the result, okay? And if you look at the quick guides for the ash RGB, and dust RGB, here's the quick guide for the ash RGB. Look at the green component, split cloud phase difference. And if you go to the dust RGB, look at the green component, right? The split cloud phase difference, okay? But in each one, you see different ranges of temperatures. For the ash, -6 to 6.3, and for the dust, -0.5 to 20, right? And that's to enhance different features, right? And as we see in the quick guide here of the ash, for example, large contribution means, no, small contribution means large water or white ice particles. And large contributions mean small water or ice particles or sulfur dioxide gas. So for example, if we choose a date with a volcanic eruption, let me put one here, 2019, July 19, 12 UTC, which is the eruption of the Ubinas volcano in the southern Peru, and change, for example, to greens. And run the RGB again. Sorry, and run the code cell again. Let's see what we can check. And here's the data. Let me send it, the data I'm going to plot right now in the chat box. Here, if you look at the southern Peru, it is very small here, but I hope you can see it. You have a large contribution here in this region, and that's because of the eruption of this volcano. Okay, however, as it is written in the quick guide for the split cloud phase, here, don't use this difference alone to identify eruptions, because as you see here, it's very hard to identify it, right? And that is why we use other differences in the ash or dust RGBs, so they can make these eruptions or dust plume much more evident, okay? So that's it for today. And we have learned how to calculate so-called BTDs, or brightness temperature differences, with Python. And usually these BTDs are used as part of RGB composites, okay? And in the beginning of each day, we should review 2 of the assignments. And on the next day, we will see the split water vapor and the split ozone channel differences, okay? And if you have any questions, just send me an email. And also, we have here in the assignment number 5, dust composite. And they also have the SO2 composite. So we will explore a little bit more eruptions in the next days. Okay. So going back to my presentation, just a moment. Let's see the GeoNetcast America's disaster capabilities. One of the main objectives of this training is that you understand the system's unique capabilities and how it can strengthen disaster resilience, right? And in this presentation, we will see the GNC-A applicability in disaster situations, considering that no internet is required. Here, no internet required. You may use a power generator or an UPS during power outages. Any member state participant of this project may become a data provider in the future, or upload or request data during disaster situations. Also, the stations could be portable, which is useful for some users, as we are going to see. And also, your antennas have a nice survival wind speed. And we will also see some user case studies, okay? So, GeoNetcast is a satellite-based system, right? And this has some advantages. And while internet, as you see here, while internet and other communications means exist, satellite broadcasts are inexpensive to operate and provide a method of communication removed from other terrestrial network limitations or periodic or possible failures, okay? And here you see a photo of the uplink in Georgia. Here's the satellite that rebroadcast data, and here's a photo of the antenna from Antigua and Barbuda. Okay? Also, the system is especially useful and efficient in providing access to environmental data in areas where the internet coverage is limited or existent. The system can be portable and products can be disseminated on demand and with low latency, making it a valuable tool in the decision-making process on severe weather events, right? And as we see here in the eTelecast ground system configuration provided by EEC, in case of local internet failure, here, data flow between the data providers of the system and GeoNetcast America's users is not interrupted because there is no internet connectivity between the downlink and the data acquisition and processing workstations, right? And in terms of data processing, once you have installed all the tools necessary for processing, internet is also not necessary. So you may keep receiving and visualizing data during an internet failure without any problems, okay? Also, GeoNetcast stations only need power for the workstations, right? And the DVB-S2 receiver here. And the DVB-S2 receiver provides power to the L&B circuitry, right? So we just need to power the receiver, okay? And in case of a power outage, the stations of the project are equipped with this equipment here, which is a UPS, or an uninterruptible power supply, which allows the station to keep running for a period of time when incoming power is interrupted. And we have more information about it in the documentation provided by EEC, right? Also, according to the documentation, UPS, we allow the system to keep running, in theory, for 30 minutes, at least 30 minutes, in the event of a main power loss. And it will also protect the station against line power fluctuations that could happen during these events. But I really, really suggest that you make periodical tests, check the real autonomy of the UPS, right? Because maybe you have much more than 30 minutes, right? And also understanding how much time the station would continue to work during a power outage is very important, right? Also, some institutions have their own generators that would serve to keep the station running, even if the UPS fails or cannot provide power anymore. And that's something that I really suggest you to do for each of your sites, okay? Here at MP, for example, we have some power generators that allow us to keep running for a considerable amount of time, even when the power is out, okay? And here's an example of a portable GeoNetcast Americas station running with a gasoline generator here. And I made this test here at NP some time ago, and it worked perfectly, right? It took approximately 40 minutes to assemble the setup, make the alignment, and this is a small 1.5 meter antenna, so the alignment was easy, and I could process and visualize the information with a notebook, also being powered by the generator or with its own battery, okay? Another nice, interesting characteristic of the system is that there are no restrictions in terms of the data format, right? This is as we have seen in the first day, this is the architecture of the system. And here you have the providers in the beginning of this broadcast chain. And here you have the users, right? And there are no restrictions in terms of the format of the data. So we could coordinate in the future data uploads by request during special events. And as we are going to see, your services may become data providers of the system in the near future, right? And as we see in this slide, apart from the data that is normally broadcast, we have the ability to add data on an ad hoc basis, meaning based on request. And the data can be prepared within or outside the region of interest, right? So this is just a matter of coordinating what to do in a disaster, for example, right? In GeoNetcast, we already have plenty of data, as we have seen in the first day in the illustrated product manual. For both GEO and LEO satellites, we have WP data, we have alerts, we have flood products, volcanic ash products, for example, and many other information that could be useful during severe events. However, supposing that a specific information is not available in GeoNetcast and would be crucial for your services and countries, we could coordinate that in the future, that your regional institutions could upload data to the system. Because as I said, there are no restrictions in terms of formats or data providers, as long as it is coordinated beforehand between these possible new data providers and the system managers, right? As I have said, we have limited bandwidth. We have 20 megabits per second, but we also have some space available. So we could coordinate that in the future with NOVA. And having regional data providers, to me, is one of the best capabilities of GeoNetcast that is not available in any other satellite-based dissemination systems. So we could coordinate with NOAA in the future how your services could become data providers, and you could coordinate among yourselves which data sets would be useful to have during emergencies, right? For example, some of you could produce value-added images and products in PNG, for example, that are small and disseminate through the system, these PNGs through the system during specific events. So other states could use them as reference. Another nice capability we still need to explore is that GeoNetcast Americas is being approved for use as an auxiliary data distribution system by the International Charter, Space and Major Disasters. And that basically means that the system may be used to broadcast commercial imagery with very high resolution for specific users of the system. So I don't know if you know the charter, but when it is activated, commercial satellite providers provide imagery related to that disaster for free. And they make this imagery available to end users using the internet. However, in the future, we could select one station per country that would be able to receive these disaster-related products. And NOAA in the uplink server may select which stations will be able to decode this information because, as I said, this could be commercial data, and there are some restrictions. But one station per country are allowed to receive these commercial data sets. Okay, so this is something for us to coordinate with NOAA in the future. And here we just have an example of some images from Landsat that have been broadcast through GNC-A and received during an emergency situation here in Brazil. So we had Landsat imagery before and after the flooding, right? And in this case, raw imagery has been broadcast. However, we can also broadcast value-added products, okay? Another very nice capability, as we saw in the second day, is that GeoNetcast Americas stations may be portable. And we have a very, very nice example and user case study from the Argentinian Air Force, right? They have a portable station here, right? It's the same photo, the same station. And it's a 1.6 meter dish that may be assembled and disassembled very fast. And they use this station in remote locations during their missions, right? And they have presented more details during the GeoNetcast Americas user webinar, which is organized every 3 months to share experiences and provide updates for users. And Ricardo, which is our contact from the Air Force, said that the stations doesn't require much power because, as we saw, we just need to power the receiver, the computer. They use this gasoline generator here, which has an autonomy between 6 and 8 hours, which is sufficient for their applications and missions, okay? And here you may see how they deploy their equipment using these storage cases here. And another nice detail is that they use these wireless point-to-point bridge here and here up to a distance of 2 kilometers. And as we are going to see today, the receiver of the project, which is the same model used by the Air Force here, it has an Ethernet connection, right? So they are able to connect this receiver, this wireless equipment, and they may have their mobile antenna at a distance of up to 2 kilometers from the workstation, which is great for their purposes, right? And you may check the presentation, specific presentation from the Argentinian Air Force and many other presentations from other users at this link here, right? As we are going to see on the last day of this training. If you access the blog, if you go to user interaction, user case studies, you see all these presentations from GeoNetcast Americas users, okay? Including this one from Argentina. And when you click at any of these images, you see information, who they are, what they do, how they assemble a scheme with their wireless connection deployments, right, that they have done. Okay, so going back, and to finish, here we have a case study from our colleagues from INSMAT, the Meteorology Institute from Cuba. They have a GeoNetcast Americas station, and they also use a 3-meter antenna, exactly as the antennas of the project. And it is the same model, right? In the market, it is known as Prodelin 3-meter, but EEC calls it the e-telecast dish, right? But in the market, it's Prodelin 3-meter dish, right? And it's the same model. And during Hurricane Irma, in this example, they're able to keep receiving data and processing and visualizing information, even with the 120 kilometers per hour winds that hasn't damaged or moved their antenna. And you may see here an animation created by Insmat during this event and where the antenna is located. Okay, and as we have seen in the antenna's specifications, the survival wind speed is 201 kilometers per hour, which in this case was sufficient to resist this hurricane, right? And another nice detail is that our colleagues from Insmat, and I have interacted with them a lot, and I still interact with them. They are producing their own imagery, as you may see here. They have defined a subregion from the full disk, right? They have reprojected the image. They have inserted the logo here, and many other possibilities, as we are seeing in our hands-on activity. So this image here have been produced by them, okay? And that's it for this session. And the idea of this presentation is that you understand the advantages of the system that you have access right now, and that with some coordination, you may have a very powerful tool during severe weather events, okay? And now we are going to explore the receiver of our ground stations. And if you have any questions, any questions, any comments on any ideas for the future, you may send your questions in the chat, or you may send me an email with your questions, okay? All right, let's go to our next presentation. And let me just open it, just a moment. Presentation number 2. Okay, the second session, we are going to explore just a moment. In the second session, we are going to explore the NOVRA S300D receiver, which is probably the most important equipment of a GeoNetcast Americas station in terms of future verification or maintenance, because this is the first equipment you take a look at. If you notice something is wrong with your stations, or if for some reason you stop receiving data, okay? And as we are going to see this week, depending on the status of this receiver, you have an idea of what is happening and what the cause is, okay? First, we will understand what DVB, or digital video broadcast technology, is. Then we will take a look at the receiver specifications, how it communicates with the workstation, how to configure the receiver, and how to monitor the reception parameters, okay? Could you please just confirm that you are hearing me well and seeing my slides? I have a little problem with my Wi-Fi connection. Could you please just confirm that you're still hearing me? Okay. Okay. Digital video broadcasting, or DVB, right? DVB is basically a set of standards for digital television. And that is the technology used by GeoNetcast. And in a summary, in the early 90s, some European broadcasters and regulatory bodies, they formed a group to discuss introducing digital television throughout Europe. And this was a brand new technology back then, right? And the outcomes of this group originated what later became the DVB project, okay? And these standards basically define what's going to be used for compression of audio, for example, compression of video, encoding, decoding, among other technological aspects of that technology. And within this framework, we have variety of standards. So we have, for example, DVB-S-E here for digital terrestrial television, DVB-C for cable television, DVB-SH for handheld devices, and DVB-S for digital video broadcast satellite, for satellite television. And DVB-S2 is the second generation of this technology. And it has a significant better performance, and it allowed to increase available bitrate of the satellite transponders. And in the end, the second generation provides an overall performance gain of around 30% in comparison to the first generation. And 3 years ago, on July 2020, GeoNetcast Americas transition from VBS, first generation, to the VBS2. And this allowed the system, as you see here, right, increase the bandwidth, that is the bitrate capacity from 12 megabits per second to 20 megabits per second, using the same satellite, Intelsat 21 in our case. And users that already had a VBS2 compatible receiver, just like the S300D, they just needed to reconfigure the receiver. But they could use the same antennas, the same LNBs, and the same alignment, which has a great benefit back then during this transition. These kind of transitions are not easy to do because the community needs to change things. But the impact here was minimum because they just need to reconfigure their receivers. And we are going to see how they can do that and how you can do that in the future. And just to exemplify and make it easier for you to understand, these commercial satellites, they have a lot of transponders, right? Dozens of transponders. And these transponders are used to rebroadcast information. And in this example, right, I have pointed my antenna to the IS-21 satellite and connected the output of my LNB in this equipment here, which is called a satellite meter, right? And the satellite meter was able to decode information from the GeoNetcast Americas transponder, which is transponder 19C. And this transponder downlinks information, as we have seen, at 4080 megahertz in the vertical polarization. In both polarizations, vertical and horizontal, but in this case, we are seeing the channels that broadcast in the vertical polarization. And as you may see here on this list, apart from the GeoNetcast Americas signal, it also downlinks a signal from other digital television channels. And some of these channels are closed, and you need an equipment as we have at our homes, for example, to watch television, right? And these equipments decrypt the signal so we can watch these channels, right, at our homes. However, some of these channels are open, and that is why I was able to decode and actually watch some of these channels in my satellite meter, as we are seeing in this photo, right? This is an open channel, Korean Central Television, for example, just to exemplify, okay? And here, I have connected a spectral analyzer, which is this equipment here, and it is used to measure the strengths of an RF signal, a radio frequency signal, over a band of frequencies. And here, at the x-axis, we have the frequencies, and on the y-axis, we have the signal strength. So I have connected here the output of my LNB, and here you may see all these peaks, right, from different transponders that rebroadcast information through Intelsat 21. And one of these peaks here, right, is the GeoNetcast Americas signal at 4080 megahertz. So the conclusion is that we need an equipment to filter this information, get only the GeoNetcast Americas signal, and forward this information to the fast client on our workstations, right? And that's the job of our DVB-S2 receiver. which converts the downlink from GeoNetcast, which has already been amplified by the LNB and had the frequency reduced from C-band to L-band. And it converts this signal, data stream, to data that can be managed by the fast client in our workstations, okay? And that is why in the ground system, we have the DVB-S2 receiver between the output of our LNBs, right? And the data acquisition server. So this equipment is constantly receiving this L-band signal from the LNB and converting the signal to something manageable by the data acquisition server, okay? And that is why during a verification, as we're going to see this Wednesday, it is the first equipment we should look at when we have any problems, because depending on the status of the equipment, we'll go this side here, or we will go to this side here in our verification. So this is a very important equipment, right? This is the receiver, model S300D, manufactured by NOVRA Technologies. And if you want a receiver to process the information of GeoNetcast Americas, we need a model like this one that is compatible with the GNC-A downlink, right? Here we have the GNC-A downlink: frequency, data rate, modulation, polarization, symbol rate, FAC, data format, and packet identifier, or PID, right? And on the right side, we have the specifications of this receiver. And if we pay attention, the receiving frequency, right, that is calculated by subtracting the GNC-A downlink frequency of 4080 by the LNB local oscillator frequency of 5150 megahertz, and the result is 1070 megahertz. This frequency here is within the range of the receiver, so that's okay. Also, GeoNetcast America's data rate of 20 megabits per second is lower than the maximum data throughput of the receiver, which is 80 megabits per second, right? So you will be able to use the receiver even when NOAA increases the system bandwidth, which, as we have seen, the system bandwidth is scalable, and it could increase in the next years, depending on the user requirements, okay? Also, the modulation, the symbol rate, the FAC, forward error correction, data format, and the other parameters are totally compatible with this receiver model, or the receiver model is compatible with these parameters. But it's important to mention also that any DVB-S2 receiver that meets these specifications may be used for GeoNetcast Americas. And as we mentioned last week, the S300D is the most popular model among the community, right? It's easy to configure and has an Ethernet connection, which facilitates things a lot, right? However, there are other receiver models being used by the community, as you see here, that use other communication interfaces like USB, as in this model here, CI, as in this model here, or this, and PCI Express, this one and this one here, okay? However, based on my experience, external units like this one or units from the project, they are by far the best ones in terms of configuration and in terms of maintenance, okay? The other model used by the community that has an Ethernet connectivity is this one here, black unit called the SR1, manufactured by Ayeka, which is a company from Israel. And this is another very nice receiver, okay? And the cheapest receiver is this green model here in the middle, here, called the Technisat SkyStar S2. And it costs something around $20, okay? It is manufactured in Germany. It's not that easy to find, right? And I know Argentina is using one of these models, and I also have one of these too, okay? Okay, now let's understand how we may connect to the receiver. This is how the receiver is connected to the data acquisition workstation. Your data acquisition workstation, it has two network cards, right? One here for the local network, and the other here to communicate with the receiver. And in the receiver's back panel, we have three connections, right? The power input here on the right, the Ethernet port near the power input, the satellite RF input on the left. So I have a receiver here. Right? Here it is, the NOVRA S300D. And if you look at the back panel, you have the power input here, the Ethernet connector, and the satellite RF input. Okay, let me turn my receiver on. This is a spare receiver. Let me turn it on. You see that the power light now is red, right? Because we will learn how to configure it and monitor the parameters, right? And the output of the LNB here, the output of the LNB is connected to the satellite RF input through the IF coaxial cable or the intermediate frequency cable that is connected here. And to make this connection, we use this connector, which is called the F-type RF connector, like this one here. Okay? So that is why the receiver is connected to your workstations, and that is how the LNB is connected to the receiver. Okay? Also, the LNB, it needs power for the circuitry, right? For the amplification and other signal processing. So the receiver provides power to the LNB through this cable here, okay? And to communicate with the fast client, which is the ingestion software that is installed in the data acquisition server, we need to use a crossover network cable, like this one I have here, right? This is a crossover cable, right? Here. A very important detail is that the IP address of the receiver and the IP address of the network card of the workstation must reside in the same subnet, or there must be a route that connects both of them through a router. This is not the case of the stations of the project. The receiver is connected directly to the workstation, okay? And another information is that the default IP address of the receiver or the factory IP address for all the units of this project is 192.168.0.11. So if you do not change default IP address, right, IP of your network card must reside on this subnet, 192.168.0, as you're seeing here, 192.168.0, and that's a print screen of my station at NPay, right? So they are both on the same subnet, and that allows them to communicate with each other, okay? In fact, to operate the station the way they are right now, you don't even need to know this information, right? They are simply working. However, for future maintenance and verifications, this is very important because, for example, if you need to connect your laptop to the receiver to make some verifications, you need to configure the network card of the laptop so it is able to communicate with the receiver, okay? And here we have a screenshot of the data acquisition workstation from Granada, okay? And as you may see, they have two network cards. They are identified as Ethernet 0 and Ethernet 1. And that's the same situation for all the ground stations of the project. And here you have the Proteus software running, right? Processing information. And here you have the Showcast software running, also processing information. So you have different options to visualize data in your ground station. And you also have the option to create your own plots. So endless possibilities, okay? And in your workstations, Internet 0 here, ETH0, is used for the local area network. And through it, you may access the internet, share files, etc. And Ethernet 1 or ETH1, this network card is used to communicate with the receiver. As you may see here, at the configuration of this network card, the IP address of this card is 192.168.0.100. So the receiver, which has the IP 192.168.0.11, resides on the same subnet. And with subnet, I'm mentioning these first three numbers here, okay? And that is why the workstation is able to communicate with the receiver, okay? And here we have a photo of a real S300D receiver, like the one used in the project. And you may see that the satellite RF input here is connected to the coaxial cable. You see the Ethernet port with the crossover cable, and you see the power plug, right? Connected to the power source. And it is very important to know the IP address of the receiver because you will need it when the software, when you use the software to monitor the parameters, as we are going to see later, okay? Okay, now let's see how to configure this specific receiver and monitor the parameters, because this is very, very important for you to know for the future, okay? And we have two options to configure or monitor the S300D. And both options work on Linux here, on Linux, on Windows, right? There is a software called the GNC-A, which is a command line tool. And there is another software called the NOVRA Management Console. And it has graphical interface. Both softwares are free. Both softwares are provided by NOVRA. And you may download both of them on these links here, okay? And in the stations of the project, EEC has used the NOVRA Management Console here, which is the graphical interface option here on the right? It's important for you to know both options because in possible future activities, you could need to install this software in another computer, right? And as we are going to see, installing them is not hard, especially this tool here, CMCS, right? And if you want to use this CMCS tool, it's just a matter of downloading the zip file, extracting the zip file, running the executable file, right? You see here this prompt where you may insert your commands. However, you may also use the graphical interface, and installing this interface is also not hard if you are using Windows. If you are using Linux, as in the stations of the project, the installation procedure is a little bit more extensive, but it also works, right? And that happens because NOVRA developed this software for Windows only, right? Not for Linux. And if you want to run it on Linux, you need to install before that another software called Wine, which allows Windows apps to run on Linux. And that's what EEC did. And in your stations, you don't need to install it because it is already installed, it is already configured, and it is already communicating with the receiver, as we are going to see later. And finally, we have a very important information here. We have very detailed procedures available. If you need to install one of these options from scratch, and if you need to configure the receiver in another machine in the future. And I just would like to stop here for a moment to show these procedures that are available in the blog. Let me open it here. Paste the link. And this is the procedure for the Linux installation, right? And as you see here, we have all the steps. We have the GeoNetcast downlink information, and we have a section called using the command line tool, right? And you have all the steps here, like downloading the file, right? Decompressing the file in Linux, installing the CMCS utility in Linux, executing the utility in Linux, and making a connection with the receiver, as we are going to see, and reading or configuring the receiver with the GeoNetcast America's downlink information. And you don't need to do that with the receivers now. However, I remember you have some spare units donated by NOAA, and these are not configured. So if you need to configure them from scratch, this is how you do it, okay? And after that, after you make the configuration and connection to your workstations, the power button should be on, the power light, sorry, should be on. The lock light should be on, meaning that it has the GeoNetcast America signal locked, and the data LED should be blinking, meaning that it is communicating with the workstation, right? And to monitor the parameters, as we are going to see, you just need to use this command here, show satellite, and that's it, right? In this tutorial, you also have how to configure the graphical user interface from scratch. And step number 1, download it from the NOVRA software, from the NOVRA site. Step number 2, I show here how you may download and install Wine from scratch in a Linux machine, right? So you have all the procedures here. And in the end, how you may run the software, okay? How you may create a desktop shortcut, same way you have in your stations, and how you may connect to the receiver and see the parameters. And also how you may configure the receiver using the graphical interface instead of using the command line tool. So you have everything you need here. For example, if you have a station, if you want to assemble a station from zero today, and you do not want a turnkey solution, you may use this procedure here to make the installations by yourselves, okay, from zero. And I have another link here. It is the same procedure for Windows, and it is much, much easier, okay? The procedure to install the CMCS tool is just a matter of downloading this information here from the NOVRA web page and extracting the executable and running it. And you see a prompt with the CMCS utility. And the same way as we did with Linux, we may log in and connect to the receivers and retrieve information with the show satellite command and configure it if needed. And for using the graphical interface in Windows, because it is a native software created to run in Linux, to run in Windows, it's much easier. You just need to run it, and that's it. It will search for the receivers connected in your network card. You need to give a good double click, insert the password, and make the connection. And the password is NOVRA with uppercase N -S2 with uppercase S. Okay? And that's it. Okay? So we have seen on these procedures. Here's a summary of the procedures, so you have this information on these slides for future reference, right? After you install the software and you run the command line tool, you see this prompt in the terminal. And when you run the NOVRA management console, you see this interface with the parameters. In this image on the right, all the parameters are blank because the receiver was not configured yet, okay? And when assembling a new station or configuring the receiver for the first time, on this slide, you have the steps needed to configure the receiver for the first time. Again, you don't need to do this now because the receivers of the project are already configured. However, it's very important to know this information because you know that you have some spare receivers from NOAA, and these are not configured. So you need to use them in the future. So if you need them in the future, you need to configure them, and that's how you do it, right? And you basically need to configure the GeoNetcast America's downlink parameters, okay? When using the command line tool, first we need to use the login command, login space, and the IP of the receiver. right? 192.168.0.11. Insert the password, in this case, NOVRA S2, which is the default password. And then you just need to configure the parameters. The technology, DVB-S2. Frequency, 1070 megahertz. Symbol rate, 30 mega samples per second. Vertical polarization, and the package identifier for GeoNetcast Americas, which is 4201. And that's it. It is configured. But if you're using the management software, which is the graphical interface, you need to do the same, but using the graphic interface windows. Okay? And here we have the GeoNetcast Americas downlink parameters. And again, how to configure them, right? The mode is the technology, DVB-S2. The symbol rate, 30 megasamples per second. Polarization, vertical. And package identification, 4201. Okay? So in the end, I think using the command line interface is easier. And in fact, almost all stations in Brazil uses the command line interface. The graphical interface is easier to understand, okay? Also, one of the advantages of the command line software is that you may create scripts and automating the monitoring of the signal, and automate the monitoring of the signal, as you can see here on this graph, right? Here we have an example of a user that managed to plot one of the parameters from the receiver. He was plotting continuously to monitor a daily decrease of the signal, as we are going to see the reason during the next day. Okay, so one of the advantages of using the command line tool option is that you can automate monitoring of the reception parameters and create alerts, for example. If the signal decreases too much, you may create an email alert for your technical staff and write, hey, please check. So that's one of the advantages, right? And after everything is configured, we need to monitor the received parameters, right? And if you're using the command line tool, after logging in with the login command, you may use the show satellite command in the terminal. And it will display all the reception parameters, like if the signal is locked, the signal strength, right? The carrier to noise ratio, which is basically the parameters you need to monitor. Now, if you're using the graphical interface, as you have in your stations, it is very easy. You just need to double click this icon here, right? Insert the password, which is NOVRA S2. And we will see this window here with all the parameters, right? The same parameters from the command line tool, but being displayed in this nice interface, right? And when everything has been properly configured, when the antenna is correctly aligned, and the LNB skew is right, and the DVB-S2 is configured to process the GNC-A signal, this is what you should see, right? The power light must be on to identify that the receiver is working. The lock light must be on to identify that the GNC-A signal is being received or locked. And the data light must be blinking, meaning that the receiver is communicating with the data acquisition workstation, okay? That's it. The goal of this presentation was that you understand what you need to install and what you need to configure to run the necessary tools to monitor the GeoNetcast Americas parameters. And as I said, you need to configure to run the necessary tools to monitor the GNC-A parameters. And this is very important to know, especially for maintenance. And as we're going to see this Wednesday, on the next day, if the reception stops for some reason, the receiver is the first equipment you should look at and check the status, okay? Now we are going to the break, and after the break, we are going to make some tests. I'm going to make a connection to my receiver. I'm going to install the software from scratch, and you will see that it's very easy. And then we will connect to the remote station, to the ground station from Granada, okay? So now we are going to the break, and we return in 15 minutes. And if you have any questions, you may send your questions in the chat box, and I will answer them after the break, okay? Thank you very much. See you in 15 minutes. Hello, everyone. Let's return from the break and start the fun part. Just a moment. Before we start, I would like to make a pause here and ask you that go to our Moodle page here. Let me close some windows here, just a moment. Please go to our Moodle page and click at the link with the day number 3 today. Please click at this link here, Processing NWP Data with Python. Please click at it. Let me log in again. You see our new COLAB notebook that we will use today and tomorrow, right? Called the NWP, GOZAR, and METAR data processing with Python, right? Please click at the link. And as we have done with the GOZAR data processing notebook, please make a copy of it so you are able to make your changes and save it, right? And you may make a copy by clicking at File, Save a Copy in Drive, okay? This will create a copy to your Google Drives, and after you create a copy, like this one I have here, you may change the name of the file, just like as we did with the GOZAR, okay? And here I'm calling it again, Diego _ and pay, etc., 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 right? The original name of the file. And I really want you to do it now because here we are processing NWP, GOZAR, and METAR. So we use more libraries and it takes more time. It takes more time for the installation, right? So when you make, when you make your copy, please go to step number 2, right? Which is the step that install all the required libraries, run it, and wait for it to finish, right? Then when step number 2 is finished, run script number 3, downloading ancillary files, right? And wait for it to finish. When it's finished, run step number 4, right? Where we download GFS samples from the Nomad server from NOAA using a Python script, okay? Please do this now. And when we start demonstrating the NWP scripts, your notebooks are ready, okay? And we, as I said, we use more libraries in this notebook because we are processing both NWP and satellite data. So it takes more time to install them. So why it's important to run it now. Another very important comment is that when you install the libraries in step number 2, and it reaches the end, you see a message here on the lower left. A black window will pop up saying that your session has crashed. Please ignore this message, right? Because it just appears because I'm restarting here. I'm restarting the COLAB runtime programmatically, which is necessary for a specific library, right? You may ignore this message. You may close this message clicking at the X, right? Because it just appears because I'm restarting the COLAB with a program, and that's normal. Close the message and continue running steps number 3, and then steps number 4, And in steps number 4, we will download data from Nomads for a whole day, right? From forecast time 0 to forecast time 24 for today. And after that, we will be ready to run demonstration scripts. Okay? Please do it now, and I will start the hands-on with the goals arc with the GeoNetcast Americas receiver. And then when we start the demonstration, your notebooks will be ready. Okay. Now let me go back to my presentation here. Let's practice. Just a moment. Can we run all scripts together, or it must be done one by one? In this case, I really suggest you do one by one, right? You can also run them together. However, due to that warning message, I really suggest that you run them separately, okay? And wait for them to finish. Run the next step, wait for it to finish, which is much faster. And run the next step, wait for it to finish. And if you do it now, for sure, when I start the demonstrations, your notebooks will all be ready, okay? Now let's practice a little bit with the VBS2 receiver. And in this activity, I want you to see how you may connect your receiver to your laptops. Check the parameters, right? And to do this, you may use a spare receiver, if available, right? Which is the ideal situation. But if not, and that's okay, you also have two options. You may connect your laptop to the receiver of your station, as we're going to see, or you may just remotely access your station and check the parameters running the NOVRA management app, right? So we will see how you may connect the receiver to your laptops. I'll show you how you may install the tools, both the command line option and the graphical interface, right? And I'm running this presentation in a Windows machine, so I'm going to demonstrate that in a Windows machine. But you have the same procedures for Linux in the blog if you need it in the future. Okay, so to make it faster, I will do it in Windows. And as you see, it's very easy. And after that, you check the parameters. And I just would like to make this demonstration because in future maintenance activities, it would help if you have these tools installed in your laptops. So you could check the status of the receiver and the status of the antenna and the LNB without the need changing or changing anything on the workstations until you are sure the LNB, the antenna, and the receivers are working properly. So this is a good practice during the maintenance. Dealing with the workstations only if you are sure you need to, okay? If you have a spare receiver, right, you just need to disconnect the RF cable, the VBS2 receiver of your station, and connect it to your spare receiver. So this input here, satellite RF input. Of course, your station will stop ingesting during this activity, but as soon as you reconnect it, it will receive data again, okay? If you do not have a spare receiver, right, you may disconnect the Ethernet cable from the workstation and connect it to your laptops, right? And as a third option, if that's not possible, or if you do not have access to a spare receiver, or if you do not have access to your receivers, you may check the parameters directly, right, in your workstations with a remote connection, or directly at the data acquisition server, okay? In any case, if you do not have any access to your station now, there's no problem, okay? I am going to make this demonstration with my notebook and my spare receiver, so you have an idea. That's the idea now, that you understand that it is totally possible and that it's not hard to do, okay? And the idea here is that you connect your spare receiver or the workstation's receiver to your laptops using a crossover network cable, like I have shown in the camera. Be able to check the parameters without the need to deal with the workstations. Of course, during the maintenance, you'll also need to install the fast client in your laptops. And we are going to see how to do that this Wednesday. But for now, understanding how to connect your receivers is sufficient. Okay? Just remember that the IP address of your receiver must reside in the same network, same subnet of the laptop's network card. And that's the case for my laptops. Let me just open my network configuration here. Control panel, network center. I have my Wi-Fi and I have this Ethernet connection here. Properties, IP version 4, properties. And as you see here, the IP address of my network card is 192.168.0.23. And this is the same subnet, 192.168.0 is the same subnet of the receiver that I have here, and I haven't changed the factory IP address of my receiver, so it is 192.168.0.11. Okay. Going back to my presentation. I have a receiver here with me, right? Here it is. And I will demonstrate how you may install the CMCS tool and the NOVRA management app and connect to your receivers. And then at the end, we will make a remote connection to the station from Granada, right? And just remembering that all these procedures for both Windows and Linux are available at the blog, okay? And the links are available on the Moodle's webpage. Let me show you. Here you have them. Configuring the S300D receiver on Linux and configuring the S300D receiver on Windows. If you click at it, here you have. Okay. All right. After installing the tools, we may check the parameters using the show satellite commands, right? The CMCS tool, or opening the main interface of the NOVRA management app, right? Now let's make a quick demonstration, right? And show how you may communicate with the receiver. What I'm going to do is I'm going to open the procedure for Windows here. This is the procedure for Windows. And as you see here, if you click at this link, you will download the command line tool called CMCS, right? And I have created a folder in my computer called CMCS, right? And it's empty for now. I will download the file. Here it's been downloaded. I will open it. And paste it here, right? I will right click it, select extract here. And here you have it, CMCS 300 executable. Let me just send the links again to the chat, so you may download it as I'm doing here, right? And if you run this software as an administrator, this is what you see. Okay, CMCS prompt, right? And as you see in the procedure, if you use the login command, you'll be able to communicate with your receiver, right? For example, login and the IP of the receiver, 011. It will ask you for a password. And the password is NOVRA with uppercase N uppercase S, 2. Okay. This is the password. And you just need to insert the password, NOVRA-S2. And this is it, right? After that, if you click, when you see CMCS and 192.168.0.11, you may use any of the commands available in the CMCS interface, right? And you have a manual and I will send a link for you later with all the commands that it's possible to use, right? But if you want to monitor the reception parameters, you just need to insert show satellite. And this is it. It is very simple, okay? It will show you the MAC address of your unit, the technology that the receiver is using, in this case, the VBS2, the frequency, the intermediate frequency, right? After the LNB, 1070, and many other parameters. And the important ones are these one: signal lock, uncorruptible rate, carrier to noise signal, and signal strength. Of course, I do not have an antenna here with me, and that is why you are seeing off, 0, 0, not available, and minus 100 dBm, because I do not have my antenna here to connect with my receiver. But if I had, you would see all these parameters from my antenna, okay? And that's how you use the command line option, all right? Now, I'm going to download a graphical option from this link. It's being downloaded. I will open it and put it in the same folder, right? I will put it here, extract it, extract here, and here you have the software. You don't need to install it. It's just a matter of double-clicking it. It is being executed. It is starting. After a while, you see another window asking for the password, right? Or with a list of receivers, as you see here. Here, the software has automatically detected my receiver, right? 192.168.0.11. Okay, and if you click at it, and sorry, if you give a double click, you see this window here where you need to insert your password, right? NOVRA-S2. And here you have NOVRA Management Console software, right? And here you have the same parameters you had in the command line option, okay? But using this very nice graphical interface, okay? And if you are using receiver for the first time, you need to configure the receiver. And if you follow the steps from the slides here, these steps here, you will be able to configure a receiver from zero. My receiver is already configured, so I want that now, right? But here you have, you should see here when you connect your station, the frequency, symbol rate, signal strength here, the carrier to noise ratio, which is very important, as we are going to see Wednesday. And you may configure your receiver using these parameters here: RF frequency, technology, the VBS2, the package identifier for 201, and apply your configuration. Then your receiver will be configured, and you may use the software to monitor it. Fortunately, in the stations of the project, everything is done, as we are going to see here. This is the station of the project, and this is the station from Granada. This is the main window of the data acquisition workstation, right? I am remote accessing it right now. And here you have some icons on the left, Firefox, the icon to run Proteus, the icon to open the terminal, etc. And you have this one, S300D, which is the icon that when you click at it, you will open the NOVRA management console, right? And in the blog, you have the procedure. Just a moment. That shows you how to install the software from zero, just like as EC did, right? For example, how you may create this desktop icon. And Windows is very easy. In Linux, it's a little bit harder. So if you need in the future to configure a machine from zero, that's how you do it, right? And we have a question on the chat. So we can run the GeoNetcast on any computer you like. Well, if you need to, for some reason, in the future, you don't want to use the workstations of the project anymore, you may have other workstations and other computers install the NOVRA management console, install the fast software, and that's it. You will start receiving data from the GeoNetcast system, right? And as I said in the second day, to receive data, you don't need a very powerful computer, right? However, to process and manage the data, you need a computer with much better specs, like the ones you have in the project, okay? But it is totally possible to receive data in any computer, right? And I have made a test with this notebook that I am presenting it, and that I'm making this presentation, and I was able to ingest data without any problems, okay? So here, the workstation from Granada, you have the Proteus software, and it is processing the data, as you see here, May 8th, right? 1430 UTC, right? That is, they scan from 1430 to 1440. Okay, that was the last image processed by Proteus, right? And here you have Showcast running, and here you have all these plots being generated with Python, right? Okay. Okay. And also you have this software here, which is the NOVRA management software, right? Which I have just shown in my computer. However, I do not have an antenna connected to it. But here you have an antenna connected to it in Granada. And here you may see the parameters, right? For example, the signal strength, higher the better, as we are going to see in Wednesday. The carrier frequency, right, 1070 megahertz, as we have seen in the downlinks and the system downlink. The symbol rate, approximately 30 megasamples per second. Modulation, total packets received, right? You see here, more than 3 million packets in these statistics here. Ethernet receiver errors, no errors since the beginning of the reception, right? Packets processed, since we have started these statistics here, 2 billion packets, right? That's a lot of data, okay? And this is also a very important number, the bit error rate, and lower the better. And this should be 0 or something very approximate to 0, right? And here you have the carrier to noise ratio, right? And the carrier to noise ratio is the ratio between the amount of signal you have from GeoNetcast and the amount of noise. And higher, the better. We usually recommend value better than 10 dBs, right? And you have more than 12 dBs, which is good, okay? So here is how you monitor here is how you monitor the parameters of your stations, okay? And that's what I would like to show you today, right? Why is the send so much higher than the receive it for internet? Good question. I don't know. This is the total Ethernet packet sent to the fast client. This is the total packets received, maybe because the NOVRA receiver is making some processing after these packages are received, right? I think that's the cause. It is receiving the packages, making some processing, and sending these packages already processed, and that may increase the number of the packets to the fast client. Okay? So that's it. This is the software you need to monitor the incoming parameters, right? And this is a very important software, and the receiver is a very important equipment for future maintenance activities. Okay, and that's it for hands-on today. We have seen in this presentation that you may install the tools necessary to communicate with your receivers and the commands or steps you need to use to monitor the reception parameters. And as I said, this is very, very important for future activities, right? And now we are going to start the Python hands-on activities. And before we proceed, let me see if you have any questions. We have another question. Would it be wise to have a backup receiver just in case it fails? Yes, yes. It is very important that you have a backup receiver. And as far as I know, there are some spare units donated by NOAA for each one of the participants of the project, right? So you need to check the status of the distribution of the donated units. Okay, thank you very much, Eugene, for your question. All right, please check that. And now we are going to start the Python hands-on. Let me just close this presentation here. Close my remote connection. And open my presentation. Just a moment. I hope your notebooks are ready, right? To check if they are ready, you may go to the script number 1 and click at play. Here, script number 1, after step number 4, okay? In script number 1, as you see, we will list all the variables that's inside a grid file, from GFS, from Word, from any model you want to process, okay? So if you click at play and don't see any errors and see the variables being listed here in the output cell, your notebook's ready. And if they're not ready, if you're getting some kind of error, just let me know. You may send it on the chat and you check, okay? So now, let's begin. Okay, now we are going to start our, our new journey, right? And learn how to access and process numerical weather prediction data. And as it happened on the GOES-R data processing hands-on, we will start with very basic examples, right? Very simple scripts. And as we advance the scripts, they will become more and more complex, okay? So it's very important that you understand all the steps and the purpose of every command since the beginning, since the first examples. And if you do not understand some of the concepts I'm going to show, please send your questions on the chat box. You may send me a message on Google, or you may email me after the training, right? If you have any questions or comments, just like as we did, right? I'm receiving some questions from you. And I'm very happy that I have received a couple of emails in the last 30 minutes from a participant that is already processing some RGBs, the true color, the natural color RGBs, and we are trying to solve some of the problems he's facing. But right now we could solve the problems, right? So we will continue our communication so he's able to progress, right? And that's the idea, right? So let's begin. And in this first part of this hands-on, we are going to start from the basic concepts, just as we did with the goals are hands-on. And you will see that many of the instructions are very similar. We will begin reading the available variables or available WP fields that are available in a grid file or GFS in this case, but it could be any other model you are working, right? And then we will start from zero again, learning how to make a basic plot, read the pixel values, right? Read the metadata, add maps, shape files, just as we did with GOZAR, right? So if you do not understand some of the concepts or commands used to do that, you have an opportunity to review these commands, okay? And after learning the basics, we will start learning specific commands, right? To work with NWP data, like how to plot contours, how to plot string lines, how to plot vectors, how to plot bars, and many other things as time allows us. And we have plenty of time, okay? So, and the objective of this hands-on is the same. It's the same from the goals are, that you understand the possibilities of having access to digital files, right? In this case, grid files, and having total control of your data. In this case, with a programming language like Python, okay? And here we have some example plots created by my colleagues here at Entry. And they participated in a similar training a couple of years ago, right? And they are meteorologists, and they are not from the technical staff, and they didn't have much experience with Python. But after the training, they were able to produce very nice images, as you're seeing here, right? According to their needs, okay? So these examples here have been produced by my colleague, Regina, to analyze a subtropical storm called Haoni back in 2021, right? And an interesting thing is that now they are able to test different combinations, different overlays, and if a given final product is useful for them. After that, they can ask their technical staff to make these products operational, right? And they are able to provide example scripts. So makes the process much faster and easier for both meteorologists and the technical staff, right? So everyone is benefited if you learn what you're going to see on the next days, okay? This is an example provided by my colleague, meteorologist from MPIG. His name is Marcos. And here we have some other examples produced by him. And he's creating this plot to analyze the intertropical convergence zone. Okay? These are some of the plots created by him. And here we have a couple of plots created by another meteorologist, Diogo Arcego in this case. And this is for birth, right? And we didn't, interesting thing is that we didn't cover these specific kinds of plots during the training. But he was able to go beyond and test new libraries and test new modules. And that's the idea, so that you are able to understand the basics and are able to go beyond and develop your own value-added products and information, products for your med services, okay? So that's the goal of this presentation today. And for this hands-on, we also have a complementary activity or a pre-course activity that is available in Moodle. And with this tutorial, just as we have one to process GOZAR imagery locally, we also see how to process NWP image locally, installing the necessary tools in your computers, right? Let me just show you where the activity is. Here it is, complementary activities, processing NWP data with Python. You click here, Here it is, right? Getting started with Python and NWP data. And you have the learning objectives. You have the prerequisites. You have the installation steps. First, installing Conda, right? The download link. How to do it for Windows or Linux. How to create a Python virtual environment and install the libraries, all the libraries that we will need for this activity, right? And if you have done, one important comment here, if you have already done the procedure for GOLAB, you don't need to do these steps. You can right away, you can start processing testing the scripts right away, right? The NWP scripts, if you have already installed the libraries in the GOLAB procedure, okay? How you may create this environment, how you may activate this programming environment, right? How you may download a text editor like Notepad++, which is the editor I'm using for these examples. And on the next days, we will learn how to use a much better environment, right? But for now, we are using this one. After that, show you how you may download data from the Nomad server, from NOAA, right? As we are going to see later, right? File selection, level selection, variable selection, subregion, and download, right? All the parameters you need to select. And finally, download a file, okay? And here I say that you may also download this information or you have access to this information from your GeoNetcast America's ground station. It's there, right? And then we start with all the scripts, knowing the available variables, basic plot, and so on, okay? So you have a very detailed procedure available in the blog to execute the first 8 or 9 scripts from Google COLAB, okay? So that's the procedure, and if you're interested and if you want to check how you may run these scripts in your machines, that's where you should look, okay? And just as we did with GOLAB, it is possible to run the same scripts in your computers or in the cloud. And during this hands-on, we are going to see how to run them in the cloud. So it's easier for you. And you don't need to try to install these tools in your computers. Or if you haven't managed to do it, as some of you wrote me saying that you had problems, there's no problem. You may do that directly in the cloud, okay? And in the procedure available, as I have said, you see the objectives of the activities, the installations of the tools that are necessary to run the scripts, how to access the GFS samples from the Nomad server and from GeoNetcast Americas, and finally how to run the scripts. Okay. Yeah. Oh, and the password here is workshop. The password for this procedure is workshop. And the same password of the GOLAB procedure. Okay. And just as it happened with the GOLAB hands-on, we are not going to cover all the scripts, right? Because we have some priorities. However, all the scripts are explained in the slide deck, and the slide deck is available for you to download, right? So if you are interested in a particular script that we are not going to see today, you may download the slide deck, try the script for yourselves, and if you have any questions, just let me know, right? And it is also important to mention that the procedure in the blog, we see how to download data from Nomad. However, we also have GFS data in your GeoNetcast America's ground stations, right? So you have degree data for Central America and the Caribbean region, and also for South America, right? And these data sets are inside the MARN El Salvador. So our colleagues from MARN, they are downloading this data from Nomads. They are cropping these zip files and uploading it to GeoNetcast Americas as a data provider, because this information is also useful for them, right? Because they download this information from in one of their facilities, but the other facilities use this data as well. So they are using GeoNetcast to broadcast this data for the other stations. And that's basically the idea that we need to coordinate, that we could coordinate in the future. Upload data sets that are important for your services too, okay? And we also have 1 degree global data. In this case, both for GFS, and the global files are available under the ISCS GRIB2 folder. Okay, and I remember someone asking in the first day that if you have ECMWF data in GeoNetcast Americas, and we do not have, because NOAA didn't receive any requests from users asking for it, right? And as we have seen, it's possible to request new products as a user, okay? We have some questions. Oh, and it is the same question, right? At the same time, will you be able to access data from ECMWF? And the answer is that for now it's not possible, but you could make a request for NOAA, and we will see in the last day the means to make those requests officially. Okay. And just to review the steps to download data from the Nomad server, right? In this case, here's a link. Let me open it here. And send the link for you. Here it is. And when you access the link, you have many options to download data, right? Including quarter degree, half degree, 1 degree, and many other options. And it's also possible to select the region. It's possible to select the levels and the variables, right? And download files only with the variables you need. So the files are smaller. So you can subset and crop the original GRIB files and select the variables you want to download. So when you download them, it's smaller, okay? Also, in the Nomad server, you have the data set for the last 10 days, right? And these are the steps for you to download data from there. You need to select the desired data, select a date from the last 10 days, select the run, the model cycle run, right? And finally access the download interface, okay? And finally, you need to select the file you want. And if you want, for example, for analysis or forecast hour or +3 hours or +6 hours, here's how you select it, right? You may select levels you want. If you want all, you just click all. If you do not want all the levels, you might just select the levels you want, right? You may also select what variables you want to download, right? But if you want all, just click at all, right? And also you may select the region, the sub-region you want to download, right? Left longitude, right longitude, top latitude, bottom latitude. And after you made all these selections, you may also click here, show the URL or the server address for that particular image, right? And by checking this URL for the Nomad server is how I have created the Python script that download data from the Nomad server, as you see it in the COLAB notebook, step number 4, okay? If you look at the Python notebook, step number 4, you have a script here called download GFS data from the Nomad server, okay? And basically in this script, you don't need to understand how it works now. We are going to explain it later. Basically, I'm using this library here called requests. Make a connection with the Nomad server, and then I'm specifying the parameters: longitudes, latitudes, resolution, model cycle run, start hour, end hour, and interval. And then I'm building via code the addresses. And then the script automatically downloads the files for me. As you're seeing here, downloading GFS file, resolution, half degree, date, cycle run, forecast hour, file name. So I can use this script to download data from GFS, from the Nomad server, and I can do that using a Python script. So as you see here, we can use Python for basically anything. So we are using Python to process those R data. We are using Python to download data from Amazon. You're seeing here that we are using Python to download data from Nomads. We are processing data from GoSAR, NWP, as we are going to see today, METAR, as we are going to see Wednesday, and Friday and Monday, we are going to see how to process sea surface temperature, ocean color, fires, hotspots, and many other things. So that's the idea of this hands-on part of the course, that you understand the possibilities and that the staff of your Smart Services are motivated to learn it and use it and produce value-added content, okay? Another question, those nomads possesses an archive of GFS data. Yes. And I can share with you some links, but it's a little bit complicated because in one link they have an interval from, 2000 to 2005. In another second, 2005 to 2010, etc., etc., etc. So it's a little bit more complex to download historical data. And I still haven't implemented a single script to download any kind of, any time, any data, any interval. Okay, but it is possible. They have other servers with historical data. So the answer is yes. But during this demonstration, we are going to use only data from the last 10 days at maximum, okay? Thank you for your question, Wayne. And I'm happy that you were able to run the natural color script. Okay, so let's access Nomad and make a download, just for you to understand how it works. So I click here at GFS half degree, grid filter, and here you have the last 10 days, right? And this is for today, May 8, 2023, right? Model run cycle 0, 6, and 12. So last cycle was 12 UTC, 3 hours ago, okay? And until the end of the day, you have 18 and the first run for the second day, right? And here you have the parameters. If you want all the parameters or variables, right? If you want all the levels, right? Or if you want just a specific range of levels, right? And here, if you click at make sub-region, you may insert, for example, oh, I just want data from minus 60 to 15, that, for example, for South America, and I want data from 100 to 230 degrees. And here's what I would like you to note, that longitudes, you need to insert the longitudes with values between 0 and 360 degrees. And that's important to understand because we will need to introduce the longitudes that way in our scripts, right? And if you click at start download, sorry. Here, for example, run 0 and show URL, you see the URL or the address of that particular file. And by studying this URL, is that how I was able to create this script here to download the data, because I'm manually building this URL. For example, for if the resolution is 0.25, this is the URL variable. If the resolution is half degree, this is the URL. If the resolution is 1 degree, this is the URL. So I build this studying these links. Okay? If you click start download, your file will be downloaded here. Okay? All right. So this is how you may download data from the Nomad server manually, but we can also use scripts. Not only for nomads, if you are actually downloading data from any URL, you can reproduce that with Python. Any data you download using, accessing a web page, clicking at some link, and then downloading an information, you may create a Python script to download that information. Okay. And this is our first Python script. And just as it happened with the GoZar script, we will imagine blocks of code, right? So we can understand the structure of the scripts more easily, right? And in our first script, we will list the variables available in a grep file, right? And you may use this script to list the variables inside any model you want. I have tested it with Roof, with our models here produced at NPay, right? And this simply works, okay? In our libraries block, we have our first command, right? Where we import the pygrid library. And with this library, we are able to run the grep files, right? Remember on the first day where I have shown you the most used libraries for weather data processing. So we had there netcdf4, we had there pygrep, we had pyhdf that we are going to use on the last couple of days, and many others. So this is an advantage with Python, that you have working with Python. You can process many data sets using a single tool, just using different libraries, okay? So with pygrep, you import a library, read grep files, right? Our GFS data is in grep format. So you need a library to read grep files, and that's why we are using pygrep, right? The second command, we are using the open instruction of the pygrep library to read a GFS file, right? So we are using the open command from the pygrep library to run our GFS file. And you're creating the grep object, right? But you may call it anything you want. I'm just calling it grep, okay? And in the file name, we have GFS, model cycle runtime, in this case, 0Z, right? GRB to full, which is the naming convention for these files. The resolution, right, half degree, and the forecast hour with 3 digits, 000, okay? So we are reading this file. So we are reading this file and calling this file simply grep, right? Now our next instruction, we are creating a text file called variables.txt. And with the W argument, we are just saying that the file, if the file already exists, we will overwrite it. And we will call this text file as the F object. And F for file, but you could call it any name you want as long as you call it the same way throughout the script. And here's just another example that Python is very nice, because here we are creating a text file using code, right? And this could be useful for you in the future. If you need to open text files, create text files via code, or read text files using code, that's how you do it, right? In our next instruction, we have a for loop. This is one of the loops that we can create, right? We are saying that for each variable, this grep file, we will add this variable, the characteristics of that variable, in a new line of that text file, right? Apart from that, we will print that variable in the terminal, right? So this cycle will be repeated the number of times according to the number of the variables available in a grep file. Hundreds of times, right? More than 1,000 times, right? And after that, we will close the file with F, close parentheses, right? And by running this script, this is what you should see in the terminal. All the variables and the information about these variables, one variable per line. And as you see here, for this example file, we have 1,043 variables available for processing, right? Apart from that, a text file will be created called variables.txt with all these variables, right? And to process a grid file and plot a given field of the model, it is not necessary to list these variables. And it's not necessary to create a text file like this, right? However, we are doing this just to exemplify how I was able to understand the available variables and how I could process them, right? And the first variable we are going to process is this one, 2-meter temperature, right? And as you see here in this description, we have the variable name, right? 2-meter temperature. We have the number of the variable, 580. We have the unit, Kelvin. We have the level, 2 meter above ground, right? We have a forecast time, in this case 0, and you have the model cycle run, 0 UTC, right? However, if you do not know how your data is structured, because it may not look as it is here, this is a nice thing to do, painting all the variables. So you may take a look at it at your ECMWF or your Word model and understand how it works, okay? And you can also open this grid file with Panoply to understand more of the structure of these files. And let's make a quick demonstration, right? I'm going to access GeoNetcast Americas station from SIMS, as we have done in the first day. I'm going to access the MARN El Salvador folder, and here you have, right, these grid files being listed. And I'm going to send you the link in the chat box. And here I'm going to download the first file, which is the cycle run for 0 UTC for the Caribbean region, that is why it's CRB, and for forecast time 0. If you click at it, the file will be downloaded in your machines, right? I will open it, and let me open Panoply. Here, I have a shortcut as we have seen on the first day. I will run Panoply. I will open my folder called GeoNetcast Americas samples, as we have done on the first day. I will paste it here. This is the file I have downloaded from the GeoNetcast Americas station. And I will just add a .grib extension so Panoply is able to detect it, okay? I have just added .grib extension so Panoply is able to decode it. And with Panoply, I'm going to open it. And as you see here, just a moment. The file has been listed with Panoply. And look at the amount of variables you have inside a grid file, right? Many, just like we have seen in the text file. And for example, if I read the pressure reduced to mean sea level, I will click at it and create a plot. This is what you should see, right? And as you see, in GeoNetcast, we have these regional files, right? And these are the ones for Central America and the Caribbean region, right? And we have others for South America. And they did that to spare bandwidth, because if they broadcast everything, we would explode the bandwidth, right, with data. And here with Panoply, I can, for example, change the color scale, right? I can do anything I want. I can click at grid and have dashes instead of solid lines. I can click at contours and have solid contours, as you're seeing here, show the labels, and make many other operations. And as you see here, Panoply is very easy to explore new data sets, and you can use it to explore these data sets, right? In your research or in your job. But as you see here, we have changed the color scale. We have created a contour plot manually using a graphical interface. But now let's see how to do that using Python, right? So let me just close it and return to our script. Let's see how we can do that using Python. And just as a suggestion, with some modifications, you can check variables from another model. We will not do that now, but you can use the same script to read, for example, a grid file from WRF, okay, or from any other model you want, right? And this is our second script, where we create a basic plot. And just as we did with the GOZAR files, we have 4 blocks of code, right? Libraries, data reading and manipulation, plot configuration, image generation. And as you may see, our initial script is bigger than the initial script for GOES, right? Because the data reading and manipulation block is bigger, because we need more instructions to make a basic reading of a grid file. We need more instructions to read a grid file than to read an etcdf file. But it's also not that big, right? You can understand it. The libraries block, apart from importing the pygrid library, as we have done in the first example, we are importing the pyplot module of the matplotlib library, and we are importing it as ELT. But we may call it any way we want, as long as we call it the same in the rest of the script, okay? So that is very similar to what we have done with GOES. In our second instruction, we select the variable. Sorry, in our first instruction, we are opening the file, just like we did in the first script example. Open with pygrid, you open this GFS file, and we will create this grid object that I call it grid, but you may call it any way you want, right? In the second instruction, we select the variable you want to read. In this example, we are reading the 2-meter temperature, right? And this 0 inside brackets just means that we are reading the first index of that variable. It is not that important, but for some variables like precipitation, for example, you have multiple indices. For example, the first one for precipitation, first one that you call using a 0 is, for example, precipitation for 12 hours. The second index that you may call as 1, it's precipitation between 12 and 18 hours, etc. But most of the variables of these grid files have a single index, like this one, right? And that is why we are inserting 0 here, okay? In the next instruction, we define the extent of the data in this sequence, right? Minimum longitude, minimum latitude, maximum longitude, maximum latitude, right? But this could be in any order, as long as you use the same order in your script. And this is how you create a list in Python, right? If you go to the COLAB notebook, and let me go to the second script, create a code cell and call my list, my underscore list equal to open brackets, 1, 2, 3, 4, 5. This is a list, right? And when I print that list, print my list, it will print 1, 2, 3, 4, 5, right? And suppose I want to print the first number of this list. I will use my list 0, because Python indexes start from 0. And that is why I have 1 here, okay? If I insert 1, is my second number in the list, I will print 2. Okay, and so on. So that's how Python lists work. And we will use it for find the extent of our data, as we're seeing here. Minus 93 in this example, okay? Minus 60, minus 25, and 18 as the maximum latitude, right? Another detail is that when you are selecting your coordinates, just be sure that these coordinates are inside the range of the maximum coordinate you selected when downloading a GFS file. Because as you were seeing in the example, step number 4, I have selected a desired extent, or when you access the Nomad server, you insert your extent here. Just be sure that these numbers here are inside the maximum extent, because if you don't do that, you'll get an error, right? And just to comment, these coordinates here on the slides are different from the ones in the COLAB notebook, right? Here on these slides, I have coordinates for South America. And in the COLAB notebook, we are selecting the Caribbean region, okay? In our next instruction, we are reading 3 data sets, which I'm called TM, TNP, LETs, and LONGs, right? The first is our variable we want to read. The second, latitudes, right? Which is one of the available variables in a grep file. The third one, the longitudes, which is also one of the variables available in a grep file. We are creating 3 variables to store these data sets. First, I'm calling TM, TNP for 2-meter temperature, right? But you may call it any way you want. I'm just calling TM, TNP, right? The second and the third, the same, right? LETs will store the latitudes and LONGs will store the longitudes, right? And you also may call it any way you want, but here I'm calling LETs and LONGs. And we are using the data command from the PyGrid library to store the data set, to read and store these data sets in these variables, right? And to use the data command, we need to specify the boundaries of our information. In this case, in this order, minimum latitude, maximum latitude, minimum longitude, and maximum longitude, right? However, as we have seen in the Nomad server, they are specified as between 0 and 360, right? And in our scripts, we will work with longitudes between minus 180 to 180 to make things easier for us. And that's how we work with ghost files, for example. So we are using this convention to make things easier in the future, right? However, when connecting to nomads, you need to specify, reading a data set, you need to specify longitudes between 0 and 316. And that is why I'm summing 360 in the minimum longitudes and the maximum longitude. So it is basically converting my range from minus 180 to 180, okay? And as I have explained here, the second index of my extent list is the minimum latitude. Remember that the Python indexes start with 0. So that's my second, minimum latitude. And the third is the maximum latitude. 0, 1, 2, 3. 1 here, third here. 0, this one, second, this one, right? Okay. On our next block of code, the plot configuration block, it's very similar to what we had for GOES-R. It's nearly identical. We define the dimensions of our plot with the fixed size argument, right? And we plot the information with the imshow command, right? For the pyplot, from the pyplot module. And we pass some arguments. First, the data we want to plot, 2-meter temperature in this case, and we also inform the origin of this data, right? lower in this case. Remember, the origin for the goals is upper, but for GFS is lower. And I will explain that a little bit more. And after that, we select our color map, jet in this case. And finally, on the next block, just as I did with the goals, I generate my PNG with any name I want inside brackets, right? And in my last instruction, I open the plot in an interactive window, okay? And talking about the origin, and we specify lower, meaning that the origin of my data is on the bottom left side, meaning that my array of latitudes start from lower values, as we can see with panoply. My latitudes start with lower values and increase, right? If I open panoply again and open my grid file, you see, let me quickly open it for you, just for you to understand it better. When I open my latitude data set, which is called lat, and create a plot, you see that it starts with lower latitudes and increase until the maximum latitude for that file. And that is why in my Python script, I need to specify lower origin, right? Otherwise, my plot will be flipped upside down, okay? This should be our result. You have your variable being plotted with the selected color map, jet in this case. And remember, we had more than 5,000 rows and 5,000 columns in our Go16 2-kilometer files, right? And look here, we have just 80 rows and 120 columns in this example. And that is because we are manipulating a GFS file with half degree resolution, right? More than 50 kilometers, which is very low. And when you execute this script locally, you may see the temperature or the unit of the variable you're reading by moving the mouse cursor over the image. And let me just demonstrate again how you may run scripts locally. In this case, you process GFS, right? I have my terminal here. And now you go to my CD, VLab /Python/NWP. And now you activate the virtual environment on the activate workshop, which is where we have installed all the libraries, as we have seen in that procedure. And I will run script number 1, which is this one, script number 2, sorry, which is this one I have created in this editor called Notepad++, in this case, right? So you will run the second script with Python and the name of the script, Python script 2. And in some seconds, you should see, here it is. Have you seen how faster it processed the file in comparison to the goals file? And that's because we are dealing with a small data set, only 80 rows or 120 columns. That's why it's much faster. When you move your mouse over the pixels, you see here in the upper left, the temperature values, because we are reading the 2-meter temperature field, okay? And that's it, right? That's how you run your scripts in your machines. Going back to the slide. Let me find it here. I have a bunch of windows open. Here it is. Here it is, right? And here are some quick modifications. We can change the region as long as it is inside the maximum coordinates of my file. And I'm plotting the maximum region that I have downloaded. So if I change it, I should have a sub-region of this plot, not a bigger region, right? I can also change the plot size and change the variable. Let's make some tests with Google COLAB. And I want you to try to run these steps with me. So this is our first script. And if I click here at play, you see the variables being listed here in the output. Look how many variables, more than 1,000. And here we have our second script. And here we are reading the 2-meter temperature. And this is our result, okay? I can change the size of my plot. Let me make it a little bit bigger, simpler 10. I can change the region. So let me select a smaller region, -70 to -50 as longitudes and 10 to 30 as the latitudes. So I have a 20 per 20 degree plot, right? If I run it, you see a smaller region here, right? And look how pixelated it is. And I can change, for example, the variable I want to read. For example, precipitation rate, which is one of the variables that I have listed in the variables text file, and run it again. Here it is, the precipitation rate. Oh, and one detail that I forgot to mention is that in my script, I'm downloading data, in this example, from yesterday, just to be sure that data will be available there, right? But you could download data from today, for example. But here I'm downloading data from yesterday, right? Daytime today minus 1 day, yesterday. Okay? So this is from yesterday. Remember that we have data from the last 10 days in the Nomad server. And here it is. So I have just quickly changed the level, the variable, and the region of my plot. But it is still very ugly. Let's make it a little bit, let's work on it, right? And let me return to the original code. You can return your additions, your changes with Control Z. Look, I'm returning to the original state of my cell and running it again. So it is as on my original plot. Okay, here it is. And this is our script number 3. And in this script, we are doing a lot of stuff, right? We will learn how to read the metadata, just as we did with GOES-R using the netcdf library, but we are going to use the PyGrid library. We will learn how to make a basic calculation. We will learn how to add a color palette, how to add legends and a title, very similar to what we did with GOES-R. So if you didn't understand any of the aspects from the GOES-R scripts, this is another opportunity for you to understand. And if you still do not understand, you may send me an email and I can explain these instructions for you in more detail. And in these blue boxes, we have the instructions that have been added in comparison to the previous script, right? So in this first blue box, after we read the variable and create the GRB or GRIB object, we are reading the metadata. And in the second blue box, we are adding a color bar and a title, right? Just as we did with GOES-R. This is exactly what we did with GOES-R, right? Now let's explain the new instructions. Right after reading the variable, here, right after reading the variable, I read from the metadata the analysis date and store it in a variable called init, right? The second information I read from the metadata is the model run cycle called hour, right? And I store it in a variable called run. The third variable I read from the metadata is the forecast time, which is a variable called forecast time. And I store it in a variable called ftime. Then I read the valid date for that forecast and store it in a variable called valid, right? Analysis date, forecast cycle hour, forecast time, and valid date, right? And after that, at this point, we have 4 variables with information about my file. And in the next instructions, I just print all this information, right? And in the model cycle run here, the second instruction, please note that I use the zfuel instruction. And that means that I want 2 digits to be printed. Even if my hour is zero or 6 or any number less than 10, I want it with 2 digits, right? Let me just make a demonstration in COLAB. Let me create a new cell code here. And for example, number is equal to 9. Print number. And run the code. Here you see number 9. However, if I print number.zfuel 3 or 2, this is what you should see, 09. And if I run number 3, you see 009. And if I put 10, you see 10 zeros before 9. This is simple, but it may be very, very useful in the development, as we are going to see later, okay? Another thing that we are doing, it's here. We are converting from Kelvin to Celsius, just as I did with the brightness temperatures from the goals files, right? And then I define the fixed size, the imp show, and create the color bar. And for the color bar, inform the title, in this case, 2 meter temperature, degrees Celsius. If I want to extend, just like as we did with goals, if I want to extend the outliers of my color bar with the on both sides, right? The orientation, in this case, horizontal, and the distance from my main plot, in this case, 5% on the x-axis and 5% on the y-axis, right? And I have created a title, a couple of titles. GFS, 2 meter temperature, in bold, size 10 on the left. And the valid time, valid space, the valid variable that I have read from the metadata on the right side, right? And I create an image called image_3.png and show it in a interactive window, right? And this should be my result. An image with a title on the left called 2 meter temperature, the valid date on the right? In this case, March 19th, where the date that I have developed this PowerPoint, 2023, 0 UTC, okay? And one thing to clarify is, how do I know? How do I know the variables, the name of the variables? Look at the amount of variables that stores information from the metadata. Just like as it happened with the GOES-R and the netcdf4 library. And I can print those using this instruction, grb.keys, parentheses, right? And in the output, I can see all the information I may read in the metadata, including the analysis date, the model run cycle, the forecast time, the valid date. So there are, as you see here, dozens of parameters more. So let's make a test in Google COLAB. If I add here, for example, anywhere after reading the grep file, print grb.keys, parentheses, and run the script, you see here a list of parameters I have. okay? And please note that I have also changed the color map from jet to rainbow, right? And as I have mentioned, Matplotlib has a variety of standard color maps. Here we have all these variables that I can read from the metadata, okay? And I have also changed the color maps, and as I have mentioned in the first presentation, the goals are hands-on. We have lots of standard color maps, uniform sequential color maps, divergent color maps, cyclic color maps, qualitative color maps, and miscellaneous color maps, right? So here are some quick modifications we can do, like changing the color map, changing the color bar, changing the title, and reading other metadata, right? So let's make some quick changes in COLAB. So I'm going to change the dimensions here. 15, 15. I'm going to change my color map, and you may see Matplotlib color maps. You may see a list of the available color maps here at this link that I'm going to send you in the chat. And you have all the available color maps. And let me use, let me see. I will use this one, for example, gist and car, okay? Gist and car. I also can change the orientation of the color bar to vertical. I can also read other parameters from the metadata, for example, max. I will create a variable called max to read the maximum temperature of that data set, which is one of the parameters available in the metadata. Max, GRB maximum, and maximum is the number of the variable. Mean, GRB minimum, and AVG average, right? And I will print the maximum temp is comma max, right? Mean and average, maximum, minimum, and average. Max, mean, and AVG, and run the script again. So I will see in my output code, look, the maximum temperature is 311 Kelvin, the minimum temperature 280, and the average temperature for that particular time and date and file 297 degrees. And that's available in the metadata as well. And here I have the changes: vertical orientation and new color scale. Yeah, this is still very ugly, but we will learn how to make it beautiful, right? And this is our script number 4. And we will learn how to add maps with Cartopy. And we already know how to do that, right? However, here we have some changes, because for GOES-R, we were using the geostationary projection, right? And here we are using the equidistant projection. So we have a new code here, a new code here, in comparison to the previous script, right? We import Cartopy, right? In our libraries block, right? Import Cartopy as CRS, or Coordinate Reference System. And we will also import NumPy to calculate the interval of our grid lines, as we will see. Data gridding and manipulation block is the same, but our plot configuration block is different, right? We have the Cardopy projection, and in this case, it's not geostationary like with GOES, right? But it is what Cardopy calls the Plaid-Curie projection, right? And if we access the Cardopy list of projections, Cardopy projections, you see that we have many projections and options, right? Monoid, orthographic, Robinson, sinusoidal, stereographic, etc., and geostationary here. And our first option is this, Plaid-Curie, right? And that's what we are saying here, right? Then we declare the extent of our data. Cardopy needs to know the extent of our data. Our goals are, we had those big numbers, remember that? Which you need to calculate given the geostationary projection. But in the Plaid-Curie projection, it's much easier. I just need to inform this sequence, minimum longitude, maximum longitude, minimum latitude, and maximum latitude, right? And we are saying that on the first index of my extent list, we have the minimum longitude, and so on. Minimum longitude, maximum longitude, minimum latitude, maximum latitude. That's how Cardopy accepts the extent of the data, right? After that, create coastlines, borders, and grid lines, just as we did with goals are. The country goals, the continent coastlines, the country borders, and the grid lines. However, there is a new thing here. One thing that is different from the goals are scripts is that now I am manually defining the interval of my grid lines for both longitudes and latitudes. And I'm doing that with the NumPy arrange command. Remember we demonstrated the arrange command on the first day or the second day? I'm just creating a list called x logs and y logs between minus 180 to 180 with 5 as interval. And for the longitudes, for the latitudes, minus 90 to 90 with a 5-degree interval, and passing these parameters to the grid lines command, right? Just for me to demonstrate again how the arrange command works, I may create another code cell here. And for example, import NumPy as NP, my numbers. I will create a variable called my numbers equal to NumPy arrange 0 and 1. And that will create a list of numbers, my numbers, between 0 and 9, that is last number minus 1, with an interval of 1. As you're seeing here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So when I'm doing here, when I'm doing this with Cardopy, I'm just creating a couple of lists as this, minus 180 to 180 with interval of 5. And I will have this big list of numbers saying where I want my grid lines to be put in, right? In my final plot. Okay, and that's how the arrange command works. So I'm just telling Cardopy where I want to show the latitude and longitude labels in my plot, right? And here, I have a couple of commands that are new, called top labels and right labels, right? For the grid lines, I'm creating the GL object. GL is equal to grid lines. And then I'm just saying that, hey, I don't want to show labels over my plot. And I do not want to show the labels on the right side of my plot, right? Because here in the grid line command, I have passed the argument true, draw labels. I want to see the labels of the latitudes and longitudes, but I do not want to see them on the top or in the right position, right? And this should be my result. Now I have map over my image, and as I have informed Cartopy, the boundaries of my image with the extend variable, Cartopy is able to correctly put the map over my plot. And when I execute the script locally, let me do it, script number 4. When I move the mouse over the pixels, it will show the coordinates in the upper right, right? Here it is. You're seeing here, the temperature is already converted to Celsius, the coordinates, 19, 20, 62, etc. Okay? Let me close it. We could change any color of our plot using the matplotlib named colors, as we see here. As I have demonstrated in the first day, if you put here at Windows, in Google, matplotlib named colors. First link, you show you a list of all colors that you may call as a name, right? And I'm sending it in the chat box. All right. And here are some quick modifications, like changing the map colors, the line thicknesses, and also, as we have done with goals, show only specific ranges. So let's make some changes in COLAB, okay? Here's my fourth script, and this is the 2-meter temperature for yesterday, okay? I will show the labels in the 4 sides of my plot. So I put here true, just for you to see. And I will change some colors also. Red for the coastlines, blue for the borders, and white for the grid lines. Let me test it. And just remember that you can run a cell without clicking here, but clicking Control plus Enter. And I got an error. Let's see what the error is. Name error. The name tour is not defined. Let me see where it is. Here. I have inserted tour instead of true. That is why I have an error. So let me execute the cell again with Control and Enter, and let's see the result. Oh, and here I'm printing. Remember that I am printing the information from my file. And I'm doing that here. Init, run, forecast, and valid. So this is a file from May 7th, 0 UTC. And the forecast run cycle is 0. And the forecast time is 0. Therefore, the valid date is the same as the init date. Okay? And here we have, look how the labels were added here in the upper side, in the upper part of my plot. And below my plot, in all 4 sides. Okay? And I have changed the color of my map to red, right? And I can do the same thing I did with Gozar, saying, hey, I don't want to see all the temperatures. I just want to see the temperatures above 23 Celsius. Everything that is below that, I will set as NaN, right? Or not a number. Let me run the script. And this is what you're seeing here. Everything below 23 Celsius is not being shown in my plot, right? So I have total control of my data, right? In our next script, script number 5, we will read a shapefile. And that is done exactly as we have done with goals. In blue, here, we have the new commands in comparison to the previous example, right? In the beginning of the script, I'm importing the shape reader module of my Canopy library. And in the plot configuration block, I'm reading the shapefile and configuring the shapefile, exactly as we did with goals. And that's why as we are going to see until the end of this training, that reading a new product become more and more easier with time. Or processing a new product become more and more easier because as you learn, in the end, we will be reusing instructions. And that's the fun part of it, right? I'm just copying and paste. The same instructions for my goals are, for example, here, I'm using the reader function of the shape reader module of the shape of the Canopy library, specifying the name of my shapefile. And these, in this case, are the Brazilian state shapefile. And I want to see them in red, right? But in this procedure, I have the shapefile with the world, states, and provinces over the map, as in this example, right? And we configured it as red, okay? And the face color here as none, because I just want to show the contours and don't want to fill the shapefiles with color, okay? And here we have some quick modifications, like I'm changing the appearance of the shapefile and changing the shapefile to be red. And just to exemplify reading another shapefile, I will show you an example in COLAB. I have put in my Dropbox account a shapefile. And just to exemplify, let me just return the script as it was. Okay. And let me add another line of code. And I will, in my Dropbox, I have put a shapefile with the maritime regions of the world. So let me just download. And this is just for demonstration purposes. I have put this file here, my Dropbox. So I'm using the wget command from Linux, starting with an exclamation mark, because all the commands in COLAB starting with an exclamation mark is a Linux command. So I'm using the wget command to download this file, and then to the unzip command to unzip this file. If I run the cell, it is downloading the file and unzipping the file, my virtual machine, right? And if you look here, the COLAB working directory at content, right? You have this directory here and the shape files inside it. I have just downloaded with the wget and have extracted with the unzip command. So here, just to see an example that I can download to my COLAB notebook, any data set I want, as long as I have it in a server, in this case, a Dropbox server, okay? And now that I have downloaded and unzipped it, I can add this shapefile to my plot as well. I will copy. Sorry, this is script number 4. Let me run script number 5. Here you have script number 5 with the states and provinces, right? And now I'm going to copy this couple of lines to read a shapefile, to read another shapefile, right? And now the shapefile is found at this folder here and with this name here. So I will put it here, okay, between quotes. And I will change the color gray, for example, right? So I'm just copying, I have just copied a couple of instructions here and changed the file of the name of the shape file. Now run it again. And you should see the new shape file added to my final plot, right? Let's see. And here you have it. The same plot I had before, however, with a shape file. And in this example, the world marine regions, right? Under the responsibility of each country, okay? And this, just for your reference, you may download this shape file at the link I will send at the chat box for you to test later. And here we have some other examples. And here on the left, they have just only the Brazilian states, right? Because if that is sufficient for me, okay, it's faster. Remember, we learned on the second day how to add a counter to calculate how many seconds it takes to finish the script. If you're using less information, it will be plotted faster than in this case here. We will spare some seconds. And here we have some other examples, as we have seen in the first show. Those are hands-on. Now I would like to finish today with our script number 6, right? And now we are going to start learning something completely new and related to NWP data, that is plotting contours and labels, right? Until now, we are plotting the data as it is, right? As rows and columns of pixels. And we are able to show see how low resolution it is, right? However, that is not the way we plot this kind of information. We usually plot it as contours, streamlines, vectors, bars, and that is what we are going to see now, right? In this first example, we will plot contours. And what we need to add, the comments we need to add are inside these blue boxes. The blue box, it's a single blue box in comparison to the previous example here, okay? And here are the new instructions, right? First, we need to define the minimums and maximum values for our contours. And we have created a couple of variables for that called data mean and data max, right? Data mean I have set as minus 20 degrees and data max as 48 degrees. But you may use any parameters you want, right? And we also need to inform the interval of our contours. In this case, I have created the interval instruction of variable set as 2 degrees. And after that, I have created a list with NumPy. Look at it. Here it is again. The NumPy arrange command between data mean, data max, and my interval. And I have created a list of levels, which is accepted by the contour instructions from matplotlib. Okay. We also need to inform, right? Sorry. In the next command, we will start plotting the contours. And the first command is called the contour F, F for field contour, right? The second command is simply contour, meaning that is a field contour. And the third called contour label or C label, right? The labels of my contours. And I need to pass some arguments or parameters to my commands, right? In the contour F, I'm passing longitudes, latitudes, and the data I want to plot. In this case, the 2-meter temperature, right? The color map I want to use, in this case, jet, right? And the levels argument, the levels we have created with NumPy, right? If I want to extend my data beyond the minimums and the maximums, and here I'm setting both, okay? And the unfield contour command I'm passing again the longitudes, latitudes, data, 2-meter temperatures. However, I'm specifying a single color as white in this case, not a color map as jet, right? Also the line widths and levels. In the C label command, right? I'm informing first the unfilled contour I would like to reference. In this case, the image 2 object here, because I want to put labels in the unfilled contours. I set the inline argument as 1 or as true. 1 means true and 0 means false, right? Meaning that the underlying contours to be removed where the label is placed. I want the underlying contour to be removed where the label is placed. I also set inline spacing to 0, meaning that I don't want to see any spaces between the labels and the contours. The size of the labels, right? The format of the labels, meaning that I just want 1 decimal place or no decimal place, as we are going to see. And the color of my label, black in this case, or blue, or yellow, or any color you want, okay? And in my color bar instruction, I need to specify which object my color bar will be referring to. In this case, my field contour, image 1. But I may call it anything I want, right? My contour, my field contour, etc. But I need to reference the same way here. And this should be the result on the left. Now I'm seeing the data as a simple, I'm not seeing the data as a simple plot anymore, like we did with the imshow command, right? But I'm seeing it as contours, which is appropriate now. And also, in many cases, I want to show only the unfilled contours. And that is very easy, as we're going to see. I just need to comment or delete my contour or field contour command and use only the unfilled contour command and specify a color map instead of a single color, right? And here we have a couple of examples more, now for South America. Field contours on the right, on the left, and unfilled contours on the right. And these concepts will be very useful in some cases, like this one, where we are plotting the pressure reduced to mean sea level, and the thicknesses between 500 and 1,000 hectopascals. And these are unfilled contours, as you've seen here. And we already know how to plot them, right? And we are seeing some quick modifications. We can change the appearance and type of contours and labels very, very easily, as we are going to see on our next day. Okay, and we will finish today here. Let me just get out of my presentation. And that's it for today. It's already 12:30, and today we have learned how to create the night fog difference, the split cloud phase difference in our homework reflection. We have also seen the GeoNetCast America's disaster capabilities, and that internet's not required. You may use a generator or an UPS during a power outage. We have seen that we may coordinate the upload of information during an emergency situation, and that GeoNetCast stations may be portable when we have seen some user case studies. And we have also learned the details of the DVB-S technology and how to connect to and configure our receivers. And in the Python hands-on, we have started processing MWP data and manipulating GFS grid files, right? And in the next day, Wednesday, we will start a homework reflection with the split water vapor and split ozone channel differences. And we will learn more details about the ingestion software called the Fast Professional Client. And we will see the specifications of our workstations. And then in the GeoNetCast America's hands-on, we will see the maintenance checklist and a flow chart and see the critical parameters we need to monitor. And a new assignment will be proposed with the creation of advanced plots and advanced animations. And so that is why it's very important that you try to do this exercise here. Processing goals are locally, because in the homework activity proposed in Wednesday, we will need to use the tools installed in this procedure here, right? And for the next days, please do not forget to start your homework notebook and run the code cell, this code cell here, installs the necessary libraries and download the auxiliary data at least 10 minutes before we start. Okay? And thank you very much. That's it for today. Okay, do you have any questions or comments before we close?
Diego, Kathy.
Hi, Kathy.
Hi, just a quick, and it may seem like a silly question when you say locally. This again could be a local laptop, anything, and that you shouldn't need any special programming other than what you have on the Moodle site, correct?
Correct.
Okay, thank you so much.
Thank you. And I wonder if you should take the group photo today, Cassie.
Yes, I do. Okay, so everyone, I think I'm not seeing as many people as I should, but everyone, if you can turn on your cameras.
If not, we can, I don't know, between other days.
Yeah, I may have to, I'm only having 21.
Okay.
So I'm going to send out a text to everyone that photo day will definitely be on Wednesday. It has on Wednesday, we'll have a photo day. So I'm asking everyone who is participating to be here on Wednesday. Is that okay with everyone?
That's fine.
That's fine.
Mm-hmm. Thank you so much.
Like when we start a workshop, or like?
It's not when we start, because people come in. So maybe just at the break.
Yeah.
All right.
At the break, we'll have the photo.
All right. Excellent presentation again. Thank you, Diego.
Right.
Thank you very much, Eugene.
Mm-hmm.
I hope that's useful for you and your services.
I have a lot after this workshop. I have a lot of questions, lots of emails.
Okay.
Just want to understand this here first before I go into more stuff.
Okay.
All right.
Thank you.
Thank you. Have a good day, everybody.
Thank you, everyone. See you.
Thank you, everyone. Have a good afternoon.
Bye-bye.